Recording. Okay, hello. We are starting with chapter 13. I was kind of skimming through while I was waiting for it to get to 4:30. Here we are. We're starting with chapter 13. Okay, so with chapter 13, I'm hoping that people will join me along the way. So if they do, it will become a little bit more exciting in here. Just ignore that part. But yeah, with chapter 13, we're moving on further down the road and talking about compounds that have carbonyl carbons, right? So let me get right into it. We're going to be focusing on three categories of compounds, and I'm glad they looked at these together. Let me make sure the 3 point check. This is being recorded because yesterday when I got done with my recording, I couldn't find it and I panicked. I'm like, I can't do 2 hours again of this. It was there. Thank God it just popped up. I was like, okay, I can do this. Yeah, so this is recording and y'all can hear me because that's important. If you can't hear me, the recording is totally useless. And if you can't see the screen I'm sharing, that is useless too. So I can tell that I am currently sharing the screen. Yeah, that 3 point check I have to do is very critical. Anyway, let's go ahead and move along. I'll move this up here out of the way. We're looking at carboxylic acids, esters, amines, and amides. So we're technically looking at four groups, not three like I thought. We're looking at four groups together, and these have a lot in common. So when we go into this, I want to mention this right here. Why are we looking at these four groups together? Essentially, when we're looking at the chemical reactions that make esters, amines, amides, especially with the esters and the amides, you will see that technically these are offspring. They come from carboxylic acids. So carboxylic acids, we'll see down the road that the carboxylic acid, which is the organic acid, can be reacted to make esters and amides. Okay. And so this is something that we're going to be seeing down the road, and that's fine. Okay, so as usual, we start with the functional groups, identifying them. So hopefully by now you see these chapters are very trendy. They follow a pattern, they follow a trend, starting by defining what type of compound we're dealing with. We deal with structures, go into bond angles. Is it soluble in water? Is it not? What's the melting point compared to others? We're doing that whole 9 yards, right? So with carboxylic acid and esters, these are two families of organic molecules that contain the carbonyl group. Okay? Now I mentioned to you that you get esters from carboxylic acid. And I mentioned this a long time ago that when I was memorizing this list, our book was not structured like this. So we learned things kind of like things were just dumped on us. Like here's the information. And I'm like, ooh, overwhelming. And so I memorized esters as the chemicals that have a nice fragrance, like someone named Esther with nice perfume. Okay. But essentially, looking at this here, carboxylic acids react to form esters. But now we're just looking at the chemicals, right, and comparing. Carboxylic acids have the carbonyl group. By now, we're used to seeing this carbonyl, carbon double bond, oxygen with a lone pair here, that special polar bond. On one side of this carbonyl group, we have a carbon, right, with the relative number of hydrogens. On the other side, we have the OH. Now, we saw the carbonyl carbon yesterday, right? But when I say yesterday, chapter 12, but when we saw it there, we were looking at the aldehyde, right, with the rest of the molecule on this side, and we're looking at the ketone, where you had carbons on either side. Now we're looking at the carboxylic acid, where one side, right? It can be the right or the left. One side of that carbonyl carbon has an alcohol group, then the other side has the carbon and the rest of the molecule. It could be a carbon, it could be a hydrogen, depending on what we're working with here. So we identify a carboxylic acid by this combination of atoms right here. Carbonyl carbon, hydroxide on one side, carbon on the other. Okay. Now with this carbon here, you can have a carbon or you can have a hydrogen. It still counts as a carboxylic acid because it has at least a minimum number of atoms required. The right part here, this part is mandatory. Must have that. Okay. So we're working on two groups at the same time, right? On the left side, oh, well, the right side, my bad. The right side over here, we're looking at a carbonyl group. So let me make sure I summarize this. We have a carbonyl group, double bond O, then we have OH, and then we have C, right? On this side, we have a carbonyl group, we have a C, we have a O-C. So here's a carbonyl carbon attached to an OH. Here are carbonyl carbons attached to an OC. So it looks a little bit like a carbonyl and an ether if they got together, something like that. But this is called the ester. Okay? So a carbonyl group here, in the place of having the hydrogen, we have a carbon. So this combination of atoms here tells you you have an ester. So you have to have this, at least this, and this, ester. Okay? So we see this right here. Carboxylic acids contain the carboxyl group, that's the group right here. It's written as COOH, which I used to abbreviate as COO, or CO2H. You want to be familiar with all different ways because we're dealing with so many different authors here. The book author, the PowerPoint author, the exam author, and they're not necessarily all the same person, okay, or the same group. Anyway, an ester contains the alkoxy group, the OR. You, of course, have the carbonyl group, right? And the O, and then C. So you can see it as COOC or CO2C, like that. So like cook or CO2C, okay? And then we're dealing with amines and amides. I figured they did this together just because with a majors class, they don't do amines and amides together. Amides are done with the S's, but I see why they're trying to put this together here in this book because both amines have nitrogen. Amines and amides both have nitrogen. So how are they different? These are nitrogen containing organic molecules. On the left, you have the carbon attached to a nitrogen. So this one here is just a regular amine. And remember, this is the name of that guy, that financial guy that works with the district. The guy I was excited to meet. I'm like, oh my goodness, his name is amine. Do you know what it means? He's like, yeah, it's a molecule in chemistry. And then he asked me, are you buying insurance? I'm like, no, I don't have money, but I think it's cool. This is your name. He wasn't impressed, but you know what? When I did get money, I called him. I'm like, I want to do business with you because your name is Amin. Then he was impressed a little bit. I could tell he was a little amused from the right side of his face. Anyway, right. So we got the amine molecule, and then we have the amide. The amide, the carbon in the amide has that oxygen, making it a carbonyl carbon versus just a regular carbon, right? On the left, you have a regular carbon and nitrogen. So for amines, this is the magic combination we're looking for. A carbon directly attached to a nitrogen. Now, the carbon attached to a nitrogen can be attached to other carbons, other hydrogens. So we say the rest molecule would have been the blank. But this carbon here cannot be attached to oxygen via a double bond, or else that will make it an amide. So an amide, we have a carbon attached to a double bond, attached to an oxygen, or attached to an oxygen via double bond, and attached to a nitrogen. So you have this combination here. Some people abbreviate it con, or I've seen CNO. So I'm like, yeah. So when you have CN, that's amine. When you have CON or CNO, that's amide. Okay, so con. You can see in this condensed formula here, con amide. The one with no O, amine. Okay. So examples here, we have methylamine, acetamide, and these are just basic examples of these molecules. So we'll go in context and go through the naming. An amine is an organic nitrogen compound formed by replacing one or more of the hydrogen atoms of ammonia with alkyl group. So what we're looking at here is, let me add this page. If you know the structure of ammonia, ammonia has a structure here, N, H, 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 and a lone pair. This is regular ammonia, NH3. So what happens is when you replace one hydrogen with carbon, let's say CH3, we get an amine. That's what they're saying. So in other words, just pick any of the many hydrogens. I'll pick the top one and put a CH3 there. And then here we have H, and dot dot. Okay, so if I want to spread this out even more, I can say C here. We got an H, we got an H, we got an H. So remember, the CN bond is what tells us we have an amine CN bond right here. And then, of course, if the carbon attached to the nitrogen is carbonyl, that will be an amide, right? On the other hand, the amide is a carbonyl compound that contains a nitrogen atom bonded to that carbonyl carbon. So I won't really illustrate that part. I think I've done enough with that part. Oh, look at that. We're right into drawing each compound. Draw out each compound. Okay, let me pick a couple here. This one here has con, so I'm going to use that one and not do this one here. I guess they're different. So let me see. Let me start with this first one. Copy. Oh, did I copy that? Yeah, there. Okay, so with this first one here, let me see. I have 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5 carbons. Since I have 2 oxygens here, if you have 2 oxygens CO2, one of them will be part of the long chain. So I say here, one is part of the long chain, comma, the other is on the side, or it sticks out. Okay, so I'm going to put one of these oxygens here, the other one up here. They can't really all fit as part of that long chain. Okay, plus we need to have a carbonyl carbon, right? So the first carbon has got 3 hydrogens attached to it. Second carbon has 2 up and down. Third carbon has CO2. You see how this carbon has no hydrogen attached to it? No problem. Remember, it double bonds with the oxygen that's vertically up, so that's going to be taking care of the other 2 bonds that go with carbon. Then the 4th bond goes with this oxygen over here. Put your lone pair up there, your lone pair down there, move on. So we're done with this part. This carbon here has 2 hydrogens up and down. This carbon here has 3 hydrogens up, side, and down. Bam, there. Okay, not bad. Oh, do we have to decide? Yeah, this is this is an ester. How do I know it's an ester? Look at my functional groups. Once again, as usual, look for non-oxygen elements. Sorry, non-carbon, non-hydrogen. It's too early today. And that's going to be these right here. And of course, look at the combination of elements. We have oxygen attached to carbon to make carbonyl, right, via double bond. And then we have a carbon attached to an oxygen right here. So when you have this combination right here, and don't forget this right here, when you have all of this right here, COOC, this is essentially an ester. Okay. Okay, so I'm done with this one. Next one is this over here. Let me copy that, put it right here, and then we'll deal with paste image. I hate when it does this. It copied the same image. Hold on. I have to do it a certain way. Copy. Here. Paste image. Okay, finally. Correct one. Okay, this one here, because these CH3s are the outer carbons, I'm going to start my middle structure with this carbon here, right? And then you see I have 2 oxygens, so one of these will be in the middle. So I have 3 central atoms based on what I have in the structure here. Carbon, carbon, and oxygen, right? One of the oxygens has to be above the carbon right here. So let me start with my first carbon. This is my first carbon, my second carbon, then one of my oxygens will be the 3rd element in the center, right? So my first carbon has got 3 of these CH3 groups attached to it. So CH3, 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 there. So this part here is done. Then the carbon number 2, the middle carbon, the second one, it's attached to 2 oxygens. So the top one via double bond, The one on the right by a single bond. Okay, that's done. And then there's a hydrogen. So the hydrogen has to be attached to this oxygen like this. Each oxygen has to have two bonds, two lone pairs. So fill in the lone pairs, lone pair here, lone pair here, lone pair here. Done. Okay, let's look at elements that are not carbon or hydrogen for a clue to our functional group. This is my oxygen here, oxygen here. What are they attached to? There's a carbonyl carbon here. To its right, we have this bond, okay, and this hydrogen. So really all of that is important. This is normally abbreviated as cool, like that. So this up here was also CO2C, right? Or CO2H. And this is called the carboxylic acid. Carboxylic acid. Okay. Okay, let's go over here and see our last one that I'm going to be working on. This one right here. It has a lot of side groups. No need to fear. I try to be organized and systematic, at least as a teacher. In real life, I'm not that organized, but as a teacher, I try to be because I recognize people are watching what I do. So I think if you're organized and systematic, it helps out a little bit with the demystifying of the structure. Come on, paste. There. Okay. Let's try with this. The central ones, right? Because remember, CH3 are the side ones. We want to add those last, not in the beginning. My teachers will add them in the beginning, and they really confuse me. I like to add them last. So carbon will be a central one. Carbon here. I'm not sure about this oxygen. I mean, I know what it's going to be, but since we have one, for right now, I'll leave it on top. If it doesn't work out, I'll bring in the middle. Actually, here's the clue. I know it has to be on top, not in the middle, because you see how this carbon here is missing hydrogens? If it had a bunch of hydrogens, this oxygen most likely would be in the middle. But since it doesn't have hydrogens, then most likely that oxygen is on top, okay? So we'll try that. So that being the case, this is my rationale, okay? The first carbon will be in the middle. The second one will be in the middle. Oxygen will be on top. Nitrogen will also be in the middle. So I have three central atoms, okay? C O, oh no, CCN. My bad. CCN. Okay. On the first carbon, this one here, I have two CH3s attached. I'll put one on the end, CH3 right here, one on the bottom, CH3 right here. And then on the fourth part, I have a hydrogen up here. Okay, so these are done. That carbon is done. The hydrogen is done. Next, I have on the second carbon, I have an O, right? O right here, and then I have an N, O attached right here, okay? That takes care of CON. Then this N, these two groups are attached to the N on the left. So I'm going to write a bond here or draw a bond, CH3, and the bond is housing the other CH3. Okay, now remember with nitrogen, the normal bonding pattern for nitrogen, it has one lone pair. I have not finished for oxygen. Oxygen has got two lone pairs. Now everything is good according to the Lewis structure. So let me see. I see an oxygen right here. I see a nitrogen right here. I see a carbon right here. What am I seeing here? I'm seeing a con, right? So when you have CON, this is an amide. CON. Yeah, this one I skipped over will also be an AMI because you see the CON right there, right? So hopefully we can recognize that quickly just by seeing CON amide. COOH, cool, that's not acetic acid, sorry. Just the carboxylic acid, if I can spell correctly. And then this one, of course, is going to be the amide. This one is also the amide. And this is the ester right here. Okay. Oh, okay. Can you turn the air on a little bit? I'm sitting here sweating, thinking, my goodness, it's a little warm. Can you turn the air on, please? Thank you. Okay, we are now, wait. Oh, we're continuing this. Since I did a lot of the amides, I'm going to skip over the first one. This first one is kind of like the second one. Let me see. Hold on, hold on. Okay, let me see if I can do it real quick. Okay, with this one here, I'm going to try to draw this real quick. Copy, put over here. Okay, I got 1, 2, 3. I know this is on top. 4, 5, 6. Wow, 6 central atoms. Carbon, 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 3 carbons, 1 nitrogen, 1, 2. Okay, on my first carbon, 3 H's. H, H, H. On my second carbon, 2 H's. Up, down. Third carbon, oxygen, and there's missing H's, right? So double bond O. Nitrogen, I'm done with that one. Nitrogen is attached to a hydrogen, so that's going to be up here. And then you have another carbon, right? And then the carbon has 2 hydrogens up and down. Then you have a carbon here, and it has 3 hydrogens up, down, side, well, up, to the right, to the bottom, there. It seems like it's everywhere. Anyway, this is the structure. So once again, we're looking at the heteroatoms to give us a clue into what we're looking at. We see the combination here, con, right? So when you have CON, actually a carbonyl attached to a nitrogen, that's going to be an amide. I'm just using this a lot because I want you to be familiar with it and not be afraid of it when you see it out of context in a different scenario, okay? So we did this one here. I want to actually work on this right here because I'm going to run out of space. With this one here, we only have one central atom. Look at that. Our central atom is nitrogen, and it's surrounded by 3 CH3s. So I'm going to work on that right here. 1 CH3, 2 CH3, 3 CH3s. Remember, the nitrogen has a lone pair, so lone pair right here. Now, what kind of bond do we see? We see a bunch of these bonds, but we see the same type of bonds over and over again. We see nitrogen attached to carbon. The same thing over here. Same thing over here. So even though we have 3 NC bonds, this is still considered an amine because there's no carbonyl. There's no oxygen here. And there's no carbon attached to an oxygen via a double bond, right? Okay. So I'm going to go down and continue this part because I didn't want to add another page to the slides. I don't know why I did that. I know that was so random. Okay. I'm going to work on this one next, and then we'll do the other one. So central atom, based on the way this is going to be out because there's not enough hydrogen here to make in the middle. This one here, central atom, central atom, central atom. So that's my judgment, right? So I got 1, 2, 3, 4, 5. I got carbon, 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 nitrogen. Ooh, 4 carbons, 1 nitrogen. To the first carbon, I add 3 hydrogens. Up, left, bottom. Second carbon, I have to have a carbonyl, right? Because of the way the bonding looks. Okay, this is done. Third carbon, I have to add a hydrogen up and down. Fourth carbon, a hydrogen up and down. Nitrogen has 2 hydrogens up and side. Okay, then remember you have to fill in pairs. I haven't done it for oxygen. Oop, I didn't do it back here. Hold on a second. What am I doing? Yeah, you have to make sure you have an octet of all the elements that are not hydrogen, right? According to Lewis's structure. Let's see what we have here. Ooh, here's a question. Do we have an amide or not? Right? Okay. With the amide, the carbonyl has to be close to the nitrogen, right? The carbonyl carbon has to be attached to nitrogen, but they're too far. You see right here, the carbonyl carbon is attached to an oxygen, and then the nitrogen is there, but it's all the way to the right. See that? So we need the combination to be like this for this to count as an amide. It's not. For that reason, this is not an amide. What this is, so the answer is not. It's not an amide. This is an amine and a ketone. In order for us to have an amide, the carbonyl carbon has to be next to nitrogen. So let's look over here. Let's see. This here is a ketone. Okay. Okay. I've done that one. Next one. I'll do this one here next. It's an interesting one, interesting structure. They have more than one functional group, so that's very interesting. Come on, work. That's the fun thing about IT stuff. Like you're working on things and then they have a mind of their own and yeah, paste image. Okay. So as usual, this is the outer piece, right? So this is my first central atom, my second one, my third. I'm not sure about this one here. See, this one is most likely part of the longer chain because you see why? See why I'm thinking that? See how this carbon has the right number of hydrogens, so does this one here. So this will be it will be the oxygen we see here will be part of that central atom. So this would be 4, and this carbon will be 5. This would be an interesting thing to see. Okay, so nitrogen, carbon, carbon, oxygen, carbon. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The first nitrogen has got 2 groups attached to it, CH3, CH3. I'm done with this group right here. Let me put my lone pair before I forget. The carbon that's labeled number 2 has a hydrogen on top and bottom. The carbon labeled number 3 has a hydrogen on top and bottom, and then is attached to an oxygen via single bond, which is possible because this hydrogen had the right number of, sorry, the carbon had the right number of hydrogens. And over here, you have this carbon here, up, right, bottom. We have a lone pair, okay? So what I see here, COC, COC is an ester group. Sorry, not ester. This is an ether group. COOC is an ester. This is an ether group. And over here, we're fine. Over here, we have NC, NC, NC. This is an amine group. Okay, I'm going to spend some time on that to make sure that you guys are comfortable with that. Right after the structure, we now move on to naming carboxylic acids. We will name carboxylic acid using the IUPAC system we saw before. So we'll containing the carboxylic carbon, the whole group, and then we will name it like we would cane, replace the E with O. Apparently, all organic compounds, their ends with oic acid. All right. Number the chain carboxylic group at carbon 1, but omit 1 from the. You will do this all the time. So chemists are like, if we're doing this all the time, there's no need to specify carbon 1. Each time, this carbon will be carbon 1. So in the name, there's no need to point it out because it will always be implied. Okay? And apply all other nomenclature rules. It's saying, yeah, the rest of it applies. It's like, we're tired. Rest of it applies. Okay. So with this one here, you have a structure that's the carboxylic acid. How do we know that? We got a functional group right here. You start numbering, as you can see, 1, 2, 3, 4, 5, 6. So this, if it was hexane, if it was an alkane, it would be named hexane, right? But they're saying replace the E with oic acid. So let's see how that works. Hexane, replace the E, I'll take the E out, with oic acid. So it becomes hexanoic acid. Yeah, that's the longest chain. Okay, now what about the little branches, the side groups that were not named in the long chain? We got, let's see, 1, 2, 3, 4. We're saying we have 2 side groups. One over here is on carbon 4, so it's 2 methyl. The other one is on carbon 5, 5 methyl. See, they always want you to number from the functional group, right? If you stick with that, you're applying the same rule to all the other compounds, right? So 2 methyl, 5 methyl. So when we combine them, we start with 2, comma 5. We consolidate the side groups, right? 2, comma 5 dash dimethyl hexanoic acid. Wait, what? Oh, I'm sorry. Why did I put 2 here? It's 4. Oh my goodness. Sorry, y'all. 4,5 dash dimethylhexanoic acid. I'm like, why am I looking at 2? This is 4. There are certain days, my brain is like just, yeah. Anyway, I just have to make sure I'm just double checking my work. Okay, so we're working on naming carboxylic acid. Once again, in the life outside of the lecture, sometimes chemists come up with common names, sort of lazy names. So we want to be aware of these common names. The common name uses not oic acid like we saw with the systematic name. The common name ends with ic acid. So you want to be aware of both, right? But once again, this class will keep it simple because we are dealing with a non-majors class. So they're giving you just enough taste, right? Without pushing you in the deep end. So formic acid is an example of a common name. It's not following the systematic name. If it was systematic, having one carbon, this would be called methanoic. Okay, meth will be one carbon, right? And then oic, yeah. But it's called formic acid. This is the one that ants spit on you whenever they bite you. Bite, spit, right? I know you're probably thinking gross. Acetic acid. We love this, maybe we hate it. This is vinegar. Okay. The technical term or the IUPAC name for this is ethanoic acid. So acetic acid, which is a more common name, is actually the common name. This is the one that's mostly used. If you want to be formal, you would say ethanoic acid, but the more common name that's used is acetic acid. And then we also have benzoic acid. Once again, you have the benzene ring right here. So yeah, just be aware of these common names. Oh, right there. We jump right into it, right? No warm up. Okay, we're gonna be given the IUPAC. They don't want you to do the common names. We gotta use the systematic names. How come they use this name, but they want us to do IUPAC? Because that's what they want us to learn, right? The process. Okay, let me see if I can add a page here so I can be prepared with the space I need. Add a page. Yep. Once again, in case you're wondering, I'm using an app, Notability. It is free. I don't get royalties for this. I like free things. Okay, so what I'm working on here, let's see, numbering. I want this drawn out, so I'm just going to copy this, y'all. At least for the carboxylic part, I want it drawn out. I'll do it on the side here. 1, 2, 3, 4, 5, 6. So I'm going to draw it on the side here. 1, 2, 3, 4, 5, 6. Okay. This is the one that has the carboxyl group. And then let's see. I shouldn't have counted that way because y'all know the rule says start from the carbonyl carbon, right? Or the carboxylic carbon. So I shouldn't have really counted it that way. That's okay. We'll be fine. So on this first carbon, you have your carboxylic carbon. We're good. And then 1, 2, 3. On the third carbon, you have 2 methyl groups like that. And of course, the rest of these are H's, right? I didn't have to draw these out. I just want to make sure that I am numbering these well, okay? So our longest chain starts from this group right here all the way to there. And we got what? 1, 2, 3, 1, 2, 3, 4, 5, 6. 6. So 6 is hexane, right? Replace the E with oic acid, so hexanoic acid. Let me write this a little smaller. Hexanoic acid. You don't have to specify what carbon because it will always be on the edge. Okay, and then what about the side groups? We have 2 side groups, both on carbon 3, right? So we have a 3-methyl, another 3-methyl, right? On carbon 3, we have 2 methyls. So when we consolidate these, we get 3, 3-dimethyl. Systematically, right? That will be our first one. So since I've drawn this here and used all that space, let me make this smaller because apparently I can't write small right there. Okay, for this second one, I think I can do it right here, right? I think I can. So recognize that this right here is essentially this. OH, right? We're dealing with this. This is our first carbon, our second carbon, third, fourth carbon. Then we have a side group. So with 5 carbons, we have essentially pentane will be the name. Replace the E with oic acid. Okay. So let me actually just erase that and write on the side pentanoic acid. And then let's come back and see. We have a side group on carbon 4. So that will be 4 in organic. A side group chlorine is called chloro, 4-chloro. So 4-chloro pentanoic acid. Okay. You want to scoop these together because they usually letters are usually not separated. So 4-chloropentanoic acid. It's the numbers that they separate because I want to make sure that you don't confuse them as a bigger number than they are. Okay. Oh, this one here I have to draw. So I'm going to draw this on the bottom, right? Oh, this is interesting. This is my carbon, as usual. My carbon 1, 2, 3, 4. And then there's all these attached. So I have to redraw this. 1, 2, 3, 4. Technically, this is carbon 1, 2, 3, 4, right? And on the right of carbon 1, I have OOH. So since I have 2 O's, one has to be on top, the other one has to be on the right, attached to the H right here. I'll draw it like that. So these are done. On carbon 2, this carbon right here, I have a hydrogen on the bottom, and on top, I'll write this vertically, CH2, since I don't really have a lot of space, CH3. So this part and this part is done. On carbon 3, I just have 2 H's, H, H. On carbon 4, I have an H right there, right? So I'm done with 3, I'm done with 4. Okay, but on carbon 4, I also have these 2 groups. I have CH2 CH3, right? So I put one on my left, the other one I put on the bottom. I need the space right here. CH2 CH3. Okay, finally, I'm done with all of these. Now this looks a lot better. So now I can find my longest chain. My longest chain goes from here all the way to here. Okay, but we're only counting the carbons. Please notice I'm only counting the carbons to figure out the name. Those those prefixes, not prefixes, but the names, pent, meth, all that stuff refers to number of carbons. So to number this, 1, 2, 3, 4, 5, 6. I have 6 carbons in my longest chain. 6 carbons, we usually have the alkane name of hexane. Replace the E with oic acid. See how I changed that without canceling anything out? Hexanoic acid. Okay, that takes care of this part. Now I have 2 side groups. One on carbon 2 right here. So this is going to be 2-ethyl because I have 2 carbons. One on carbon 4 right here, 4-ethyl. Okay, how do I bring this together? They're the same side groups. So it's going to be 2, 4 diethyl. Ooh, hexanoic acid. Let me bring that closer because I'm not good with space. There. 2, 4 diethyl hexanoic acid. Between 2 numbers, put a comma so you don't communicate 24. You don't put a dot, you put a comma. And then between yeah, you can't just make up your own stuff. These people voted and we didn't get to vote, so it's done. It's done. We have to follow this format. If you put a dot, the exam will mark you wrong because that's not, what is it called? That's not acceptable, right? You can't just make up your own abbreviations and stuff. So yeah, 2, 4 diethyl hexanoic acid. Okay, let's see. Oh, I forget we don't have answers here. Okay, y'all. Let me pick one that is interesting. So what I'm going to do is, I'm not going to do this one here, but we can do that one. We'll do the last 3, or the remaining 3. How about that? Let me add a page down here to make it easier. I'll actually copy all of this. copy, and try to find an interesting way to paste this. Hold on. And then copy again. Oh, this is just copy. It's not working the way I thought it was going to work. That's okay. Oh, I actually do want to do cut. Hold on. Let me just copy the regular way. It's not working very well for me. Copy that. Paste. And I can delete this whole thing. It's the small things, y'all. It's the small things. Why is this not working? Come on. Copy. I'm trying to find a more efficient way to transfer this over without having to copy and paste everything one at a time. Come on. Okay, so now I have this twice. It's okay. I'll just go ahead and cut. Can I just cut this? Now it works. I don't know what I have to do to make the cut feature work. Because when I tap it, the first thing that comes up is, oh, okay. Cut. Okay. Ah, you know what? Let me just work on the first one because this is taking too long. Okay. 2-bromobutanoic acid. So we're now working on drawing our own structure, right? So butane means 4 carbon. Oic acid. Okay, we can do that. So carboxylic acid will be the first. Well, the carboxylic carbon will be the first one. I'll put my OH here. This is my first carbon. Since I need to have 4 carbons total, I'll add 3 more carbons. 1, 2, 3. I'll deal with that whenever I'm done. So this makes a total of 4, right? Okay. On the second carbon, this one here, I need a bromine. Okay? And then fill the rest of it with hydrogen. So I put a hydrogen here, a hydrogen here, a hydrogen here, a hydrogen here, and a hydrogen here. Okay? Now I have to deal with this thing. They used to have it one way that was a lot simpler, and then they stopped doing it that way. So now this has become, let me cut this whole thing. I don't want it there anymore. What they're doing right now has become just unnecessarily complicated. So I have to go through here and copy each of these each time. Copy. Okay, we'll do it this way. Okay, next one we're working on is this one here. Again, start from the right. Octanoic. Wow, 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. You're kind of numbering backwards, right? Our carboxylic acid is right here. We got our OH right here. So this part is done. 5,5-dimethyl. Where's carbon 5? Methyl, right? So this part is done. Oh, I have to put in my H3s there. And then 2, this carbon here, ethyl. So I'm going to write this up. CH2, CH3. Then you can fill in the rest of them with hydrogens. Our teacher used to allow us to leave them without the hydrogens. But no, you want to fill in the hydrogens because y'all are doing homework on a computer. The computer is not gracious. Computer is a program that will just mark you wrong if you left things out. So just since we're doing online stuff, it's easy just to see things the way they're supposed to be. This is our structure. I know it looks a little busy, but this is it. We have our 2 side groups right here on carbon 5, 1 side group on carbon 2, and we're done, right? Okay, so here I need my last one. That will be 3, 4, 5. Wow, that's a lot of side groups. Tetraethyl. Whoa, I need a lot of space for this. Decanoic. Deca means 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, double bond OH because it's an acid, right? To get rid of that. Okay. Tetra means 4. Ethyl. Wow. On carbon 3. So let me number this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On carbon 3, you need 2 side groups. On carbon 4, you need not 2 side groups, but 2 2 carbons. So that's the SO. Carbon 5. Wow. Carbon 6. Okay. So the rest of these are CH3. I'm going to write them in a more condensed form. CH2, CH2, CH2. When we come here, we have a H down here, and H down here, and H down here, and H down here, and H down here. And of course, the bonds that fill these in, like that. Okay, up here we have CH2, CH3. CH2 for the middle piece, CH3 for the end piece. CH2 middle, CH3 end, CH2 middle, CH3 end. And here we have that. Okay. Whew. That was a trip, but we got them all, right? 3, 4, 5, 6 tetra. Okay. We're now moving on to the ester. With the ester, we're going to name the ester using IUPAC system. Name the R group bonded to the oxygen atom as an alkyl. That's the part that's kind of tricky, right? We have 2 components to this kind of functional group, which is a little different from the other ones. You're going to name this part here as an alkyl group, and then name this part here, and they tell you name this part here as a carboxylic acid. And then when you do that, replace, I know, oic with 8. Actually, OH. Or the way they say, replace ic with 8. Okay? So we're going to work through this step by step. You're going to have 2 parts of the name. The side group here is your alkyl group. So hopefully they'll keep it simple. I have to keep an eye out for this one to make sure I'm keeping it simple. So for example, give the IUPAC name for the following ester. Remember, name this as an alkyl group, then name the rest of this in a way that it ends with O8. Okay, so I'll just say you're going to name it like an alkane, and then replace it with O8. I feel like that's a lot easier than to name it as an acid and then name it as an O8. That makes it just very complicated. Okay, so the alkyl group we have here is going to be, of course, the methyl. They show that to us over here. This is called the methyl group. We've just named this part here as methyl, 1 carbon methyl. The rest of this here, let's see if this works. If this was a alkane with 4 carbons, it would be butane, right? And then you replace the E with O8 to get butanoate. Let's see if it works. Does it work? Yeah. Why don't we stick with that? I don't know why they have us name it as an acid just to name it as a ester. I just feel like that's too many steps. Just take the alkane name, replace the E with OH. That's just 2 steps. If you go from alkane to acid, from acid to OH, that's just going to be 3 steps. Too many steps, right? So name it as an alkane, replace the E with the OH, and that makes the ester. So it's going to be methyl butanoate. I know. That's already interesting. But good thing you have access to your information right here. Once again, with this one, it may not feel like it, but we kept it simple. I'm like, what? All these carbons. Right. Trust me, with organic, the majors class, there are all these branch groups. There are things hanging here, iso groups. It gets more complicated than this. But let's follow the principles, right? I'm not going to try to do any fancy transfers, just simple copy and paste. Okay, let's see. So I'm going to draw this out so I can know how I'm going to break this up. There's a carbon here and a carbon here. Okay, this is my functional group carbon, the carbonyl carbon. To the right, there's 1 carbon. Then here we have 4 carbons, and then we have 5. So my goodness, we end up with 1, 2, 3, plus 4, 7 carbons and 1 oxygen in the middle. Wow. Okay, I can do this. 1, 2, 3, 4, 5, 6. an oxygen, and the 7th carbon, right? I think I got everything. Okay, so let me start with this one on the right. This first carbon here is attached to 3, I'll leave it as is, attached to 3 hydrogens, right? This part is done. This carbon here is attached to an oxygen on the right, you see that? And a carbonyl on the bottom. So remember, when there are 2 oxygens to the right of the carbon, one is above with that carbonyl bond, then the other one is to the right. So I have this right here, lone pair, lone pair, lone pair, lone pair. So this part is done. I have these 3, oh sorry, not 3, 4 CH2s. So I got CH2, 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 CH2. I'm trying to keep it in the condensed form to make this go faster. These are my 4 CH2s. Then my last C has got 3 H's. I'll leave it like that. That works too. Okay. Now I have to name this as a side group. This will be methyl. You don't number it because it's always attached to that oxygen. Then I have to name all of this here ending with O8. So I count my carbons. 1, 2, 3, 4, 5, 6. So if it was a hex, if it was an alkane, it would be a hexane, right? I know it's kind of getting tricky, right? If it was an alkane, it would be a hexane, but it's not an alkane, so I have to replace the E with the O8. So no 8. So in front of this is hexa. I know. You can rewind that until you get it, right? Methyl hex. I'm going to pick ones where y'all don't have side groups over here. This is still, I tell myself, a non-major. Don't have, yeah, these are simple too. I'm like, it's a non-majors class, y'all. Let's keep it simple. Let's keep this friendly. Okay. Okay, paste image. Oh, come on. They copied the same one. I don't know what the deal is with these. Hold on. Copy, paste image. Okay, did it right this time. Okay, so I'm counting my carbons, right? I'll start from the right. 1, 2, 3. One of these oxygen is central. 4, 5, 6, 7, 8, 9. So my 4th element from the right is an oxygen. Let me see if I can start from the left. 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I make it? Okay. The first carbon on the right has 3 H's. I'm writing this in the condensed form, so that's done. Second carbon has 2 H's, CH2. That's done. Third carbon has 2 H's, CH2. That's done. And then we have 2 oxygen. One is part of the long group right here. The other one is a side group right there. So we got lone pair, lone pair. We're doing good. We're done with these 2 and that carbon. Then this 5th carbon over here. Is that 5th? Yeah, that looks like 5th. Yeah, that has 2 H's, CH2. The 6th has 2 H's, CH2. The 7th has 2 H's, CH2. Am I missing some here? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Oh, okay. Anyway, and then we have CH3. Why do I feel like I counted this wrong? Oh, because I included the oxygen. Okay, that's fine. That's fine. I got it. Okay. So now we have, let's see, 3 CH2s and then CH3. Then we have 3 on the right. We're doing good. I need to fill in my lone pairs here, so I feel good about this. Name this part here as an alkyl group. So as an alkyl group, this will be with 3 carbons, propyl, right? Name the rest of this as an alkane, and then convert it to the OH form, which is the ester form. So with the alkane, I have to count the number of carbons. 1, 2, 3, 4, 5. So if it was an alkane, it would be a pentane, right? But it's not really an alkane, it's an ester. So I replace the E with oic acid. No, wrong one. With O8. O8. We're not doing that extra step. Okay? I'm trying to make it simpler. Pentanoate. Okay, whew. As you can see, I don't memorize these. So when I'm working with you guys, I'm working on it fresh, you know? Okay, so propyl pentanoate is the name of the structure, right? Much fun. And then we have one more. Let me add a page just so I can be a little bit more linear, to be a little less random. Our last one here has that benzene group. That's okay. We'll follow the rules and deal with it as is. So the good thing about this, I don't have to redraw it much, right? To quickly recap this or redraw this, I have my benzene group right here. 1, 2, 3, 4, 5, 6. I have my carboxylic right here, and I have my CH2, CH3, dot, 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 dot. Okay, so I named this as an ethyl group, so that will be, I mean, the side group, it will be my ethyl, right? I named the rest of this as an ester. So if it wasn't an ester, this would just be benzene. But if it became an acid, it would be benzoic acid. Benzoic acid, sorry, benzoic acid. This is one of those times where we have to follow the longer rule because it'd be benzoic acid. I can't just go from benzene to the name I know it should be. So this is one of those times where following the long rule works because the short rule doesn't work very well. Benzene doesn't have any carbons, it doesn't have any extra carbons and oxygen. Benzoic acid has this extra carbon right here and then the OH. For the benzoic acid, it becomes, or you can just remember this as benzoate. So the name of this will be ethyl benzoate. Okay? Yeah, ethyl benzoate. So that rule of going straight from here to the benzoate doesn't really work with that. So use whatever method you need to get that. Okay, so can we go from these names to the structures? Let me pick a couple here that we can work on so I can go a little faster because these are a little different, right? Propyl propanoate. Okay, hold on. Oh, a page didn't add? Okay, paste. Okay. Then let's see if I can do, this is a common name. I'll do this one here. This one here. And the last one will be the one with the benzene. Copy. Methyl benzoate. Okay, this should be cool. Okay, so with this one here, propyl. So to the right, we know we have the separation in the molecule, right? We have the part that goes to the right over here and the part that goes to the left. So we have this right here, da 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 da. Okay, propyl goes right here. So propyl essentially has 3 carbons, 1, 2, 3, CH2, CH2, CH3. That took care of that name. Propanoate. Propanoate. This just means propane or propan means 3 carbons. So we attach 2 additional carbons to make 3 carbons. I know. Because this counts as carbon 1. We need 2 more to make 3 carbons. So I added CH2 here. I added CH3. And together we get what was converted from propane to propanoate. Okay? So remember, prop in organic chemistry means 3 carbons. So on the right over here, we need to have 3 carbons. As you can see, we have those 3 carbons. Including the carbonyl carbon, you have to have a total of 3 carbons on the left of the oxygen, right? So we have 1, 2, 3 to make the propanoate part, okay? So I hope we're doing good. Right now we have hexanoate. So let me start with this one here. First of all, I draw my functional group right here. Dot, 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 and I have a bond. To the right, I need 2 carbons with this ethyl. CH2, the inner one is usually CH2. The outer one or the edge one is CH3. CH3, right? So I'm done with this part. Hexanoid. Including this, I need to have a total of 6 carbons because hex stands for 6 carbons. 1, 2, 3, 4, 5, 6, right? I just fill in the number of hydrogens. CH2, 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 and the one on the edge is CH3. Oh, this one here is not a bond. This is just one, the first carbon. So we have a total of 6, right? 1, 1, 2, 3, 4, 5, 6. Yeah? And this will be ethyl hexanoate. Okay. Finally, methyl benzoate. So with benzoate, we have to draw a benzene ring, like we just saw. And then we have to make our carboxylic acid functional group on this side right here. Okay, dot, 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 bond, dot, 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 dot. The benzoate part is this one here. This is the benz, right? So this part is technically done, and so is the OAte. All we need is the methyl group. We put this right here, CH3. Ta-da! I know. I make it. No, when I was learning this, I was like, this is the worst thing ever. I mean, how could chemistry get worse? That was my initial reaction. Then I'm like, oh, this is the best thing ever. Organic is one of the subjects I really, really like. Really, really like. Okay. It took a while for it to warm up to me. I'm like, okay, I don't hate it anymore. Okay. So now that we've gone through all that fun stuff of drawing the structures, now we're moving on to talking about those intermolecular forces, right? We know this is polar. We know this is polar and hydrogen bonding, right? OH. So carboxylic acids and esters are both polar. But only carboxylic acid can undergo intermolecular hydrogen bonding. Do you see that here? This is a carboxylic acid. This bond here, this is polar. This bond here is a step up, and it can do hydrogen bond because it literally is an OH. It can do dipole-dipole, meaning it's polar. And it can do LDF. Polar here, carbonyl is polar and can also do LDF, right? So remember hydrogen bonding, they're showing you how carboxylic acids can hydrogen bond with each other. You see how they're hydrogen bonding here in the structure. So carboxylic acids will have a higher boiling point than the ester, of course, because the esters cannot intermolecular hydrogen bond. Any molecule that can hydrogen bond always has the highest boiling point. You're like, we've been here before. Yes, we are going here with every chapter as long as we are in the organic section. So between these two, you see here, this one, it has a CO bond, so it is dipole-dipole and LDF. This one has an OH bond, so it's going to be hydrogen bonding, dipole-dipole, and LDF. And therefore, it will have a higher boiling point, higher melting point compared to that. The intermolecular forces of attraction are very high with that one. Okay? Okay. What else? Oh, same thing. Carboxylic acids have higher boiling points than alcohols. Okay, this is a statement that we need to kind of slow down and pause. I don't want to rush through that. Okay, so far alcohol has been winning. Every time alcohol shows up, it has a high boiling point. Now we have met alcohol's match. We're told carboxylic acids have a higher boiling point than similar alcohols. What? Yeah, they can both hydrogen bond, but carboxylic acid has more hydrogen bond interaction. In other words, it has more hydrogen bonding sites. Okay, so I kind of like competition. I'm like, okay, this is making me excited right here. So they picked 2 molecules with similar molar masses. You see, they were even trying to give this one propanol a chance because do you notice how this has 3 carbons? But the carbons were not enough to help it win in this boiling point challenge. Let's see. In this structure here, we only have one site. We only have one hydrogen bonding site. That's this site right here, okay? On the other hand, with carboxylic acid, or in this case, acetic acid vinegar, this can hydrogen bond right here, one hydrogen bond site, but this C double O can hydrogen bond with another acetic acid whose hydrogen happens to be nearby. So let me try to draw this real quick. Hold on a second to make this point to show you why carboxylic acid beats alcohol. Right here. See, we have a we have a hydrogen bond right here. We have another site right here. So we have two hydrogen bond sites total on one molecule. So we have one there and one here. So total is two hydrogen bonding sites. For that reason, because we have more hydrogen bonding sites in carboxylic acid, they end up for the first time beating alcohol. Until now, alcohols have always won. But now, if you can tell from my voice, I'm smiling. Yeah. Is this as exciting as real races? No, but I teach chemistry. I have to find my where I can find it, right? So yeah, we have a new winner: acetic acid, carboxylic acid. Okay. So here they're asking you which compound in each pair has a higher boiling point. We know carboxylic acid, based on its carbonyl and its OH, has two hydrogen bonding sites, right? Versus this here, CHO is aldehyde. Remember that? Okay, so first of all, it has no hydrogen bond. It has a dipole-dipole, and it has an LDF. So over and over again, carboxylic acid wins. This is going to be the higher one of the two. Okay, we know, right? We know now. This one here does have hydrogen bond, but it only has one hydrogen bonding site. Okay. This one here, if we draw it out, has two hydrogen bonding sites. So we have a total of two hydrogen bonding sites. For that reason, this wins. This will have a higher boiling point. Okay, higher boiling point. It's nice to kind of change who wins. It's boring when the same molecule wins all the time. Everything, alcohol, higher boiling point, high melting point. So now carboxylic acid has dethroned alcohol. Okay, rank the following compounds in order of increasing boiling point. Which compound is the most water soluble? Ooh, two different questions. Which compound is the least water soluble? So we have three different questions, but the last two are somewhat related, right? So I'm going to address it one at a time. Let's look at the one with the highest boiling point. We look for carboxylic acid right there. Okay, so we know, but I want to show you this. They're saying here rank in order of increasing. So here's the thing. I'm going to share with you embarrassing things I did. Okay. As a student, I'll be so caught up in the chemistry, I'll forget the English. What does increasing exactly mean? Okay. Let's define increasing. Increasing means arrange it in order from low to the left to high, right? That's important in chemistry, right? Because I would do this and then I'll get it wrong. I'm like, but no. And my teacher would say, you arrange it in order of decreasing. And I was like, oh, I forgot to focus on that word increasing. Increasing, it says arrange in order of increasing, right? Make the low one, the low one on the left, and then make sure the high one is on the right. Okay, so this is my highest. Why? I have two hydrogen bonding sites. This is my lowest. Why? I have no dipole-dipole, no hydrogen bond. All I have is LDF because this whole molecule has just carbon and hydrogen, right? Lowest because I have LDF only. So I still haven't answered my question. To answer my question, I have to order these in increasing. So I'll go from the lowest. Wait, hold on a second. Let me cheat. Hold on. I can do this. No, sorry. Let me improvise. Can I improvise? It won't be neat, but it will work. Okay. Lowest. Because I'm trying to draw it and I'm like, this is a lot to draw it. Middle, the one in the middle, intermediate. Come on. And then this is the highest. So I have my lowest, LDF only, right? I have my middle and I have my highest. This is answering that question. Okay, you have to put the low on the left, the high on the right, or else you haven't answered the question. Okay, next one. Which compound is the most water soluble? Okay, you're comparing, right? Even though, even though I agree with you, if you're a deep thinker, even though this one here, which I'm about to draw out to you, has so many carbons, we're trying to compare it with the others, right? Dot, 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 dot. Yeah, even though this compound here, which has hydrogen bonding, has 1, 2, 3, 4, 5, 6, 7, 8 carbons, it technically has two, well, it has one hydrogen bonding site, right? But it has two polar bonds. So this should be the most water soluble. Okay, because both this polar bond and that polar bond, each of them can support up to 5 carbons, and we got 8. So this would be, of the three, this would be the most water soluble. Okay, the next one we're looking at is this middle one here, because this one looks just like this, only we have a different arrangements, right? This is most water soluble, and they said they wanted the least water soluble. Which compound is the most water soluble? Got that. Least water soluble is the one that has all those carbons and hydrogen. So let me zoom this out a little bit so I can draw it out here. So we have C, H, H. I'm just going to answer the question versus overly explain because I'm trying to be mindful of time. C, H, 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 right? So here is least water soluble because you see it has no, so here most water soluble. Why? You can say it has two polar bonds. Two polar bonds. Least water soluble. Why? No polar bonds. There's no polar bonds. There's no OH bonds. There is nothing here that makes polarity in that molecule, which water likes, because water is polar and like dissolves like, right? So I want to make sure I've answered all three questions. Yep. And so we move on. Okay, now we're looking at life outside of the lab. So we have two painkillers or anti-inflammatory agents. We have aspirin and we have other anti-inflammatory agents like ibuprofen. These are common pain relievers and they are also anti-inflammatory agents. They both contain the carboxyl group. More than that, they have the carboxyl group right here, right? But they also have the benzene group right here. But there's something important they're trying to mention here. Let me see they mention it. Oh, they don't. Okay. So one of the issues with aspirin is that the carboxyl here can irritate your stomach. Because remember it's an acid, it can irritate your stomach. So sometimes they tell you maybe take it with food, don't take it on an empty stomach. So they add other chemical agents in it to make sure it doesn't irritate your stomach too much. But if you're very sensitive, or your stomach is sensitive, that carboxylic group right there may irritate your stomach. Just FYI. Okay, so if you've had other chemistry classes, we learned before that acids react with bases to make salt and water. I remember learning this in biology also. So if you've had biology, you've learned that acids react with bases to make salt and water. So guess what? Carboxylic acids behave like other acids. They will react with bases, for example, sodium hydroxide, to form salts that are water soluble. So let me tell you all something, right? The complexity about chemistry, or in this case, organic molecules, is sometimes the organic molecule you're trying to make is nonpolar. Let me go back to what's the page right here. Is nonpolar. And as we can see here, it's not water soluble, but you want the chemical you're making to be water soluble. They have hired you. You're the scientist, you're the designer of the molecule. How do you make something that's not polar? Polar. Here is the strategy. If you can take a carboxylic acid and react it with a base, the base will make a water soluble salt. See? So you can take something that wasn't soluble to begin with and make it soluble by making it into a salt. Not just any salt, but a water soluble salt. So when we were taking organic chem, we had to know these techniques. And on the exam, you'll be asked to design a pathway. Teacher will tell you what molecule they want, and then you have to figure out how to make it to get the exact parameters set by the teacher. Man, we were competing. It was interesting. I've forgotten most of it, but it was very interesting because there was so many reactions, so many details you have to remember. Anyway, so here remember, this salt is not just any salt, it is water soluble. We'll talk about this when we get to soaps. Okay, it's important that your soap is soluble in water. Okay, where was I? Acetic acid. So here's our acetic acid. This is vinegar. We're going to react this with base. And please realize when they're separating these molecules or these compounds into parts is to help you out visualize this, right? To help you visualize this. So here, this is normally sodium hydroxide, but they separate these into ions. So you see right here, you have your sodium ion, you have your hydroxide ion. Well, what happens? Something called a replacement reaction happens where the sodium, remember from other chemistry classes, the hydrogen tends to form a positive ion, and sodium forms a positive ion. They're in the same group, group 1, positive, positive. So hydrogen can only be replaced by something else that's positive because hydrogen itself forms positive ions. So this hydrogen here cannot be replaced by OH because that's negative. You see it's negative right here. It will be replaced by Na positive. So you see the hydrogen that was here got replaced by the sodium. But what happens with the OH? The OH with the sodium goes off with the H here and they form water. So when I was learning this, I was like, man, that's a lot of information. But what I did, though, I didn't give up. I said, you know what? I have to remember, since I'm making salt and water, let me just make the water from the reactants, then the rest come together. So you see, the OH from the base takes away the H from the acid to form water. Then the Na has to go replace the H that got taken. So it's kind of like a switch, an exchange. Give me your H and I'll give you my Na. The Na ends up where the H was. These go off together. They make water molecule, and then we have the salt, water soluble. That's what they're saying here. A proton is removed from the acetic acid to form its conjugate base. The acetate ion, which is present in solution, is a sodium salt called sodium acetate. Hydroxide gains proton from or to form a neutral water. The hydroxide gains the proton from the acid to form water. Okay. So the bottom line here is I want to stick with the basics. No pun intended. I want to stick with the bottom line, right? Just to show you our goal is highlighted here. We have just been taught a powerful skill in organic chemistry, how to take something that is water insoluble and make it water soluble. I feel like if you focus on the purpose, the reaction becomes less overwhelming. Do you know how to make something that's insoluble soluble? Yeah, react it with a base. So they picked an acid that has so many carbons. It has how many? 1 plus 6 plus 1. It has 8 carbons. So this apparently is water insoluble. Their goal is to turn it into water soluble salt, water soluble carboxylic acid salt. What they do, they react it with a base. The OH goes off with the H, leaving the Na up here. So we get the water soluble salt. And then here we have our water. Okay, we can do this, right? We know the purpose, right? To go from insoluble to soluble. Weirdly enough, a lot of medications we take are in the water soluble form. So imagine if you took a medication and it wasn't water soluble. It would be hard for it to dissolve in your blood if it has to dissolve in your blood for it to work, right? So let's see, we can do this. Our goal is to make water soluble. Oh, okay. So for this first one, I meant to take this one out, but I'll just work on that. For this first one here, we know we're going to draw a product. Oh, my bad. Let me do it the way I did it when I was a student. I'll start with a simpler, easier part first. I know OH goes off with H to make water, H2O. Then the Na has to come here. So then I draw it this way. That made me feel a lot better because I could see it, right? So O now ends up with Na because Na took the place of H because H went off with OH to form water. Okay, and this is water soluble. Salt. Let's not forget that. Okay, now with this one here, we have a similar scenario here, but this one here, it gets a little bit more complicated, but let me see, do we have any other questions? I'll work on this one real quick. Same thing here. You have CH3, CH2, CH2, C double bond O. And so we have one site here for our sodium to go and attach to. Sodium is still positive here. This is negative. And then this time, though, we don't form water because this goes off with this. So essentially, we end up with a weak acid. It gets a little bit more. I'm trying to keep this simple. We end up with a weak acid. And this weak acid can react further with the sodium. So the biggest thing here I'll say is focus on this soluble product. Okay, they can use this or this. So I'm gonna check to make sure all of your other assignments just focus on this. Once again, we're trying to stick with the introductory level for this course, which is to tell you that you can take something that used to be insoluble and make it soluble by reacting it with a base, and that goal is achieved. Okay. And the base that we tend to use, the more common one, is this one here. I thought I took that one out. Okay, so this is where soap comes in, right? Hold on. I'm talking a lot. Ooh, okay. So I'll give you guys a short version of the story. Soap has been used for years, many, many years. There's some tribes. I grew up in Tanzania, East Africa, and there's some tribes there, especially the Maasai. They're hunters, and so they go out for a long time to hunt animals. And so when they do this, sometimes where they're living, they don't have a lot of access to water. Water is an issue. So what they do is they take animal fat, and since basically fats, okay, soaps are basically fats, they have animal fat with them. So they use the animal fat to cleanse themselves. Now, it may be difficult for us to relate to that because we use water soluble products. You know, we have our soft soaps, we have our hard soap, but they all dissolve in water. But technically, soap is made from fat. So they carry animal fat with them and they rub it on their body and rub it off to essentially clean themselves, to cleanse themselves. Can you imagine being in a place where you don't have water and you clean yourself by putting butter on yourself and then wiping the butter off? You're going to be very greasy. Your skin will be so shiny and smooth, but you have butter. And they have very good skin for doing that. Their skin is very smooth, but they use that because they get that soap is essentially fats. Okay. So soaps are salts of carboxylic acids that have so many carbons in a long hydrocarbon chain. And remember, when you have a hydrocarbon chain, that is a fat-like property. So the soap has two parts because soap is designed for a purpose, right? To cleanse, to clean you. It has the ionic end called the polar end, and it has the long carbon chain, which is nonpolar. This is the oily end. Okay, so soap has two ends. It has a nonpolar end that has many nonpolar bonds, carbon-carbon, single bonds, carbon-hydrogen, single bonds, and this is called the nonpolar tail. Okay, so here is the picture of our soap molecule, structure of our soap molecule. So imagine, right? Let me zoom this part in. Look at this whole part here. This is oil, nonpolar, oil-like behavior. And so this is called the nonpolar, oops, wrong thing, nonpolar tail or nonpolar end of soap. And then this used to be a carboxylic acid. You see that it got reacted to be made into a salt, right? To make this soluble. We want our salt to be soluble because unlike the men in the Maasai tribe, they rub the animal fat on themselves and then use physical means, right, to wipe it off. We don't do that. We stand below water. Now, if you had butter rubbed all over your body, butter is insoluble. So if you stand below water, if they stood below water, the water will not wash off their soap. I'm using air quotes to say soap. Their soap would have to be soluble to wash off with the water. Okay. So why do we need fatty stuff for the soap? Why do we need something that's fatty or oily? Because most dirt is oily. And so your dirt will be dissolved by this part of the soap. Isn't that neat? Okay. The oily tail is to trap dirt. And then once the dirt is trapped, it's sitting on your body just waiting for you to take a shower, to run the water. Once you run the water, because you have a polar end, the water can interact with the polar end or the ionic end and then wash off. See what they do, the Maasai do, the dirt is trapped by the oily end and they just wipe it off. They wipe it off good. Well, right? So we're told here in water, soap forms micelles. These are spherical droplets with the ionic heads on the surface. So you have these are the ionic heads right here. The green dots, these are the ionic heads. And then the inside here, this is where the dirt is trapped, right there. I mean, can you imagine how the soap molecules get together as one to trap dirt? And meanwhile, you just casually take a shower, don't even think about it. Meanwhile, all this is happening at the atomic level, right? And then dirt is trapped by all of these tails, trapped in there. It can't go anywhere. And all of a sudden, when you come out, you are fresh and clean, right? So fresh and so clean, right? Because all these tails have trapped the nonpolar dirt in the interior, and then water interacts with them and then washes out. Okay, so nonpolar hydrocarbon tails trap nonpolar materials such as grease and oil, and then of course this washes away in the presence of water. Okay, so now we move on and look at other types of reactions. We've kind of seen something like this before, right? We're seeing carboxylic acids and ester undergoing a common type of reaction called substitution. In the beginning, we took off a hydrogen and brought in a sodium. Now we're taking off this whole group right here. Whatever this letter is, they're telling you can be an OH. The whole OH group can leave, and OR will be this is for the alcohol, and this is for the ester. So I'll show you down here, right? Yeah, we have examples. So just see substitution. So think about this as when you were in high school. You know, we don't have this in college. In high school, your teacher could have a substitute, right? So if a teacher has to go somewhere, she or he gets a substitute to come in and take their place and do the same thing that they were doing. So here, imagine Z is the teacher leaving, right? Going somewhere. And then you have someone coming in the place of the teacher to substitute them. So this is called substitution. The group comes in to replace the group that's leaving and going somewhere else. It just so happens behind the scene, this group is going off with this one's partner, right? This is chemistry. This comes in and then this goes off with that partner and then we have this. But in this context here, this is not called double replacement. This is a different group of chemists. It's called substitution. Okay? And we see this kind of reaction with carboxylic acids. So over here, OH is about to be the leaving group. How do we know that? You see how they show, this is a little tricky, right? You see how they show it here? Because it's like, okay, OH left, not just the H. Because when I was a student, I'm like, I don't like looking at it that way. I like looking at it as though H left and R came in. The teacher's like, no, all of OH leaves. I'm like, oh, okay, whatever. OH left, right? So OH leaves. Now in the major class, you have to show step-by-step mechanism. So yeah, OH leaves, and then OR comes to replace OH. So you see the colors, right? OH leaves with H once again, forming water, and then OR comes in. So this is how they're showing you how you can go from carboxylic acid to an ester. Now we are learning these reactions separately, but in the majors class, they combine all these together and they tell you uh go from an alkane to a carboxylic acid. Yeah. Yeah. And you're sitting there going like, oh my goodness, how do I go from an alkane to anything at all? And then from an alkane to an alkene, you add water, you do all this stuff, and then oh, fun days, y'all. Once you get it, it's like a puzzle, right? But anyway, so OH is the leaving teacher, leaving group. The substitute is the OR. See, and that's how we make the ester because we go from the functional group like that, O dash H, and then we end up with this, and then O dash C, right? So this is carboxylic acid like we saw before. Carboxylic, if I can spell, acid, and we have the ester here. Okay, let's see actual examples. Oh, down here. So when you take acetic acid and add it to ethanol, once again, this whole group leaves, OH leaves off with hydrogen to form water. The remaining group just comes here and takes the place of OH. Okay, substitution. Make sure you have the alcohol and of course you have the acid here. Now, of course, when you guys are watching this, because you're doing this online, the approach, the way you're doing it is very different, right? You're not having to memorize all these and do a big mechanism. So I'll just say here, in order to get the ester, the carboxylic acid has to be reacted with alcohol for you to be able to get the ester plus the water. Okay? So the same thing happens here. Carboxylic acid has to be reacted with alcohol to get the ester plus the water. Okay? They use the common name here. Anyway, and then we see here, once the ester is made, I wish we had examples first. Do we have examples at some point? Oh, they're down here. I see it right here. We'll get to it. I have to be patient. Once the acid is made, you can then reverse it to get the alcohol. Actually, you know what I want to do? Give me just a moment. I really want us to practice some of this because I feel like it will make more sense once we practice it. Let's see. Yeah, let's practice some of it. This should have been right after that. So over here, I'm not going to work on each and every one of these. I want to work on a few. I want to work on this one here and then this one here. Okay. Hold on. Right here. Easier. Your brain gets a mental break of just absorbing information when you actually get to practice it out. I don't like doing so much because even I am getting fatigued. I've been talking for almost 2 hours right now, and I've had a whole day of fun, exciting get-togethers via not Zoom, but Teams. I mean meetings, right? Oh, come on. Why did it copy the same one again? Copy. Okay, finally. So what are we doing here? We are reacting these with ethanol in the presence of acids. So I have this reactant plus CH3, CH2, OH. And then here I have my acid. So I'm going to write H2SO4. That's how you write it. Same thing over here. CH3, CH2OH. And then I'm going to have my acid here. This is what they said, right? Just take this, react it with that. Okay, I know that one of these products has to be water, right? And then the way they wrote it, they actually reversed this. So what I'm going to do here to make this match what we just saw, they reversed this and wrote the H first, and then the O, CH2, CH3. Remember that part? That way, these two go off together to make H2O on the product side. And then this just comes in the place of that. So I'm going to write this on the side. Let me see. CH3 parentheses 2 CH single bond carbonyl. And then down here, O, am I going to have room? CH2 CH3. Yeah, that, like that. So this is the new group that came in, right? This is a group that came in because it was out here. Once the OH left, the leaving group left, and the OCH2, CH3 came in like the substitute and took over the OH, where OH left. Okay, over here, the same thing. You don't have to flip this formula to write it that way. I just like to stick with what they did, if it makes sense. So H, oops, H, O, CH2, CH3. I know that this whole group right here will be my substitute. Now this one here, I may have to redraw. Oh, come on. That's okay. Carbonyl OH, okay? I know this whole group is leaving. Can I use a different color? Ooh, hold on. My eyes are burning a little bit. I think it's allergies. Yeah, these two are going off together, okay? So let me actually write it in the bottom. Let me not be lazy. I'll write it like this. HOCH2, CH3, and then H2SO4. Okay, so the greens are going off together. Then the yellow would, oops, wrong color. The yellow will join the carbonyl, right? So in my product, I have this right here. If I can draw, hold on, woo, it's getting difficult here. Carbonyl, then the new group that came in was OCH2CH3 plus water. Okay? Yeah, sorry, my pictures are horrible. They're getting horrible. That's not a word, but it's just getting more horrible with time. Okay? As I'm getting more and more fatigued. But let's see. Yeah, so now that we've seen how we can get to the ester from the carboxylic acid, they're telling you, okay, now, so we're going from left to right. You can see here, carboxylic acid adds with alcohol, if I can spell. This is the alcohol group here. This is the carboxylic acid to get ester plus water. Okay, that's the general formula. You want to write this down somewhere. Carboxylic acid adds with alcohol to produce ester and water. This actually has a name in organic class, the majors class. Is called esterification, the making of the ester. And here, ester is kind of the star, the focus, right? You're making ester, so it's called esterification. But we're not going into that all that deep stuff, right? We're just kind of glossing over this. So, forward reaction, right? Well, we're being told here, look at that. You can actually reverse the reaction. What? Yeah, look at that. We can reverse this and then start from the product and get the reactants. You take your ester with the water and then kind of undo the damage that was done and get your carboxylic acid and your alcohol. That's what this is showing right here. That's why I wanted us to do some practice so we can see it. We're starting with the ester. This is the group that came in. Remember the substitute? I guess the teacher is done doing her business and she wants to, well, it could be a she or he, sorry. Mm. It, her, him, whatever. They, okay, the teacher, they want to come back. Okay. I'm done with my business. I want to come back. Okay. Now the substitute now has to be the one that's leaving. So the substitute leaves and then the OH comes back in and bumps off the substitute. So we're now going the reverse way, right? Where the OH is replacing the OR when originally the OR replaced the OH. I guess the teacher is done with his or her business and coming back. So the substitute has to go back home. And that's what happens here. So treatment of an ester with water in presence of an acid catalyst reforms, not just forms, but reforms the carboxylic acid and the molecule of alcohol that used to be the reactant. So now we're going kind of forward to the right and then from right back to the left. Okay. So we can move on and see how this happens. Now, this is called hydrolysis. And hydrolysis in chemistry is just a general way of saying hydro means water, and then lysis means break. So you're using water to break bonds. The water is necessary for this reaction. You're trying to break a bond, but water has to be present. So bonds are cleaved by the reaction with water. So let's see what's happening here. Just like before, they separate the hydroxide group that's coming in this time and the leaving group that's the ester. And so the coming group that's coming back in comes in and makes the carboxylic acid. And then hydrogen goes back and reunites with its companion, which is to make the alcohol, right? The starting material. So hopefully after seeing that, my goal is to try to make these reactions seem less scary. So I have all these extra stories and dramatic things and stuff, but I just want you to engage with the material more and not be afraid of how interesting it looks, right? What do I want to work on? I want to pick the one that's easy to write. I'm going to work on this one here. I just realized, hold on, copy. Come on, copy. I need to add a page. Yeah, I have these PowerPoint slides because normally in class, if I'm doing a face-to-face class, I'll have three and I'll have people come to the board and you see how I'm working it out? Yeah, I'll have them work it out and I'll just stand there. I'll do one and then they'll do the other two. And they'll just like be like, the other people writing on the board and then I'll check it when we're done. Oh, I'll check it. So the approach on campus is very different. So that's why I have so many questions. Okay, where was I here? Oh, they said add water with sulfuric acid. Okay. So this time, oh, do I need more space? Let me see if I can make this a little smaller because it seems it's not working. Oh, okay. I'll try to be diligent. Okay, so we're adding water, but remember, think of water as HOH. In organic chemistry, water is HOH. So this group is the one coming in this time, right? Trying to replace that group. So I'm highlighting this way. And then, of course, don't forget we need sulfuric acid as a helper. I wish it was just water, but sulfuric acid has to help water out. So we have CH3, CH2, 8 carbonyl, and then OH. Now, on the other end, since I can't write on this side, I don't have enough space. Let's see. These two go together, right? So I put the H in front of the O, CH3. So you can write it like this, or you can flip it over and write it like this. CH3OH. You want to see it both ways just because I've seen books write it both ways. You want to get back the parent alcohol and the carboxylic acid from the ester and the water. Okay, that's what I'm trying to do here. So here, let me see. I need to draw this out in a way that's useful to me. Let me do my best. I'll try to do my best here. Carbonyl, oxygen, 1, 2, 3, CH2, CH2, CH3, dot, 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 dot. Okay. We're gonna add this to water, HOH. We know OH is coming in. It's coming back from the conference, wherever she went or he went. And we're using sulfuric acid, H2SO4, to help this out. This is replacing all of that. So can I squeeze this in the right? Let me see. Carbonyl, dot, 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 OH. Yeah, that should actually be easier. And then you can write this as HOCH2, CH2, CH3, because that's visually more directly what we just did, right? The H goes off with this partner that they used to be partnering together. Or you can flip this over and this can be CH3, CH2, CH2OH, right? So we reclaimed the parent carboxylic acid and the alcohol. Okay. Oh, wow, we're right here already. Okay. This is kind of tying into your lab, so at some point you should be seeing these labs. Now we're dealing with health. Olestra is synthetic fat. So we're told triacylglycerols, a commonly naturally occurring ester, contains three ester groups. So it's called tri as in three, acylglycerol, each with a long carbon chain, okay? They're lipids, water insoluble organic compounds present in fats and oils. So triacylglycerols are usually called triglycerides versus triacylglycerol. That's kind of hard to say, triglycerides. And they say, well, don't eat too much of that, but it tastes so good. It tastes so good, y'all. Last time I talked about steak, guess what I did? I went out with my friends last Friday. Guess what I ordered, guys? Steak. Because that's all I could think about after discussing all that fat. I ordered a steak and it tasted so good. I feel so condemned, y'all. I'm sorry. Try acylglycerol right here. You can see. So you see how these R's, they have these R's here? This R. Thank you, Rihanna. I know. It's just, I'm like, I know it's bad for you, so I don't eat it all the time. I don't eat it all, but I really try. I'm like, okay, once in a while, it's a birthday. Maybe it's Friday. Right. So we're here. This part of the molecule, when they leave it as R, so in this context here, R is kind of like X. They're leaving it as a variable so they can fill in whatever they want to fill in, right? So they can fill in a bunch of carbons here. All we know is the R groups have a bunch of carbons, and this is the part that makes it very fatty and greasy right there. Okay, so we're going to be looking at this molecule here in context. So we know they're fatty. We know they're present in fats and oils, and because of that, they're not water soluble. They're going to be soluble maybe in organic compounds, but not water. Okay. Okay, so we're told animals store energy in the form of triacylglycerols, like the triglycerides, right? Using enzymes called lipases, the three ester bonds are hydrolyzed when the triacylglycerol is metabolized. So when we ingest this right here, so we're eating, as we eat that, there's an enzyme in our body called lipase that then breaks down this right here. So the breakdown, as we saw before, was between the carbonyl carbon and the oxygen. So let me go back here real quick to show y'all. When we were breaking this down, we were breaking the bond right here, right? So it's between the carbonyl carbon and the oxygen. So when this bond breaks down, now we are applying it to the body. It breaks down right here. So our lipase molecule is now doing the role of the water and the sulfuric acid, right? Because it's now happening in our body. And it's happening 3 times. It breaks down there, breaks down here, breaks down here. Okay? So diets high in fat lead to obesity. So the fake fat, olestra, also called olein, was invented to replace some of the triglycerides in snack foods, right? Once again, one of those business majors, they come in here, they hear chemistry, 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 they're thinking money, money, money. Yeah. They're like, how can I monetize this? So the lipase enzymes cannot hydrolyze olestra, right? So what they're trying to say here before I continue this is, as long as you have lipase in your body, which is a good thing, your lipase will break down fat. But then once the fat is broken down, it gets metabolized into your body, and if you're not working on it enough, it gets stored, right? Now, olestra cannot be hydrolyzed by lipase. So you eat it, all those fat-free foods, but that do have fat, they have olestra or other chemicals similar to that. So when you eat it, it passes through your body and it can't be metabolized. It passes through your body unmetabolized because lipase can't touch it. And so it provides 0 calories. So you know how those they have those 0 calorie foods, and you're like, wait a minute, but I'm eating this, right? It's okay, not that great, but it's greasy. And so that's when they have compounds like olestra, essentially showing you that the lipase is taking on the role of breaking down that molecule. So remember, just so if you're wondering how we just switched, this is the chemistry of the lab. Chemistry in the lab, sulfuric acid is the one that's helping the water, right? We don't have sulfuric acid in our body. So in our body, the role of sulfuric acid is taken on by the enzyme lipase. By the way, we're kind of switching over, oh, lipase. We're switching over to biochem. Biochem is when chemistry is now applied to your body to understand what's going on in your body. So the molecules, just so you know, will get bigger. As you can see, now we're dealing with 3 layers, right, of a molecule. Anyway, we're now dealing with hydrolysis of a triacylglycerol, hydrolysis of an acetate, right? But it's a 3-layer acetate. And this time, in the place of sulfuric acid, we have lipase. So it's doing the same thing. It's breaking the bond to release a substitute that was brought in. The bond here breaks 3 times. 1, 2, 3. And then remember, the water is essentially H-OH. For each part where the bond breaks, an OH comes in. So please notice, right? Visually, this part here is this part. I'm a visual learner, so I have to see, like, there has to be a continuum. So let me try to provide some continuum. This part here, remember, this here is your substitute that came in when you're forming the ester. So now the original molecule that was there, the OH, is coming back. So we bring in the OH, right? This OH comes back here. You see how they just put it here? 3 times. So for this reaction, we need 3 waters, 3 times. Okay, but what happens to the green portion here, the substitute? Remember, it reconnects with the H from the water to form this. Well, this is an alcohol technically, right? But we're having an alcohol that has 3 prongs or 3 legs or 3 connections. This is called glycerol. So we have glycerol here, and then we have the 3 long chain of carboxylic acid. So in the regular chemistry, we're just dealing with one level of this. In the body, it gets complicated, but we need to understand chemistry to understand our body, right? So this is what's happening as you're eating and enjoying that fat. It's breaking down, it's being metabolized. Oh, here is the structure of olestra. Look at how complex it is. So when you eat this, the lipase can't get there. There's ester groups here throughout. The ester groups are so crowded, hydrolysis can't get there because they're kind of, even though they're crowded, these nonpolar ends are blocking it, so the lipase can't get to the middle, and so it doesn't get metabolized. Okay? So smart to create a molecule with a disguise so the body can't really get to the molecule, the site, to react with it. So it just goes to the body. Yeah, let it go. Okay, so since we saw how we did that one, I think we can hydrolyze this, right? I think we can. I'm trying to see if I can. Can I cut this? Copy is not going to be good enough. Let me see. Will it allow me to cut? Come on. I need space. Okay. I'll try to do it right here. Let's see. Let me try one more time. I forget what it takes to get the other where it says cut. Ah, Okay, anyways, let me just try a new page. I need the space because this is taking up too much space right now. So I'll copy this, okay, and then make this much smaller in this page here. Oh, now that shows up. Come on, scroll down. Man, this thing is a challenge. Hold on. Okay, that's fine. I'll just work on it right here. Okay, so having this now, I know I have to break the bond between the carbonyl and the oxygen, right? Because this is holding on 3 different levels, the group that has to leave. I'm trying to bring in 3 waters. So at this top level, I'm trying to bring in an OH here. I'm bringing an OH from the other water, an OH from my third water right there. These are trying to come in. They're going to take the place of these, okay? So unlike what they did, I am going to see, can I copy this and make this slightly easy for myself? Can I copy half of this molecule? Copy. Let's see if that will work. Paste. Oh, okay. So this is kind of hard to draw on this surface. I don't have a lot of room. Okay. So here. So you see, this is the parts that got broken off, right? I'm going to leave that here so you can see. This is the parts that got broken off. So the OHs are coming in. So I'm going to draw my OH here. Dash OH. Dash OH. Dash OH for my products. So these 3 are forming this. Of course, remember lipase is the one helping us here. And then on the other side, I do have whatever got broken off. CH2-O, CH2-O, CH2-O. This is my role. So remember these open ends connect with the hydrogen. Yeah, I do apologize. It doesn't look very good, but you get the idea, right? So this ends here, connect with the hydrogen, the free ends, and then we have these 2. So we have the glycerol, and then we have the acids here. So these are usually called fatty acids. So hopefully you see that part. Okay. So we're going to our last group, I think, right? Oh, no, we have amine and amides. Okay. Our last group right here. How am I doing? I think I'm doing good with time. Okay. So with amines, we have seen these before. We talked about how we go from ammonia and then replace one of the H's with the R. Okay. This, we have the primary, secondary, and tertiary again. With primary amine, the nitrogen just got replaced, or one hydrogen was replaced by a carbon. Yeah, just one hydrogen was replaced by a carbon. So we're seeing here in the primary amine contains just one carbon nitrogen bond. So this is considered primary. It will look like this. You have a nitrogen attached to a carbon only once, and the rest of it is hydrogen. Oh, this is a lone pair here. So this is essentially primary amine. Now you can have other things here, but there's only one carbon and nitrogen bond. Okay, let me change this back to yellow. And then you have secondary amine, where there's 2 carbon and nitrogen bonds. So here you can see you have N-H, you have C here, like that. So we have 2 CN bonds, 2 carbon attached to the same nitrogen, making this a secondary amine. And then we finally have a tertiary amine. The tertiary amine, you have, as you can see here, 3 carbons attached to the same nitrogen. Nitrogen in the middle. You got your lone pair up here. I forgot my lone pair up here. And you got 3 carbons attached to this nitrogen. This time we have no hydrogen, right? So we got a bond here, and a bond here. Okay? This is how you classify primary, secondary, and tertiary. Look at the primary, secondary, and tertiary amine has has one lone pair, which is usually omitted in the condensed structure. Okay, so real quick with this one here, I guess I'll work on this one here first. In this here, I have a lone pair right here. So they're asking you, classify each amine in the following compounds as primary, secondary, or tertiary. Let me start with the easier one to identify. I have a nitrogen here, I have a carbon, I have a carbon, and a carbon. So I'm looking at the situation here, right? That looks like tertiary to me. There is no hydrogen directly attached to my nitrogen, right? It's all just carbon, so tertiary. This structure here, I have to draw it out. It looks way too complex to try to decipher right here. So let me copy this. Then we'll get into the bond angles and then go into all the stuff. Oops, I pressed the wrong one. Add page. Yeah, there. Okay, we're dealing with this one here. So central atom, really three of these, nitrogen, carbon, 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 CH2, CH2, CH2. This nitrogen here has two hydrogens. So this is done, these are done. Then I have this nitrogen attached to a hydrogen. This is done. Then I have what? CH2, 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 CH2. I'm going to have to minimize this structure. I'm running out of room. Four CH2s. Then I have a nitrogen attached to a hydrogen. Then I have CH2, CH2, CH2. Then finally my last nitrogen. Wow. Let me minimize that before I complete the structure because I think I ran out of room. Okay. So finally, I have a H here and a H here. So what are we dealing with? Okay. With this one here, since I have one nitrogen carbon bond, this is primary. This one here, I have a nitrogen carbon bond to my left, one to the right. And I can tell by how many nitrogen hydrogen bonds are left, right? So I have secondary here. Here I have one to the right, one to the left, secondary. Here I have one, oops, no, one to the left, and then these other two make this primary. Okay? That wasn't that bad once I drew it out. It was just a big structure. Okay, the geometry of nitrogen in the amine is trigonal planar, right? Do I have my, no, I don't have that page open. How do I know? We have three electron groups that are bonded and then one lone pair. So we have four electron groups. Of the four electron groups, the bonded groups are three, the lone pair groups is one. So we end up with trigonal, what they say here? Oh, pyramidal. Pyramidal. I thought I heard or I read plain. It's supposed to be pyramidal because it looks like a pyramid, right? The structure looks like a tripod stand that has lost the top of the stand. Oops, that didn't work out so well, right? Where the top part is taken off. And so the lone pair are here. And then, of course, you have your CH3, H, H with the N in the middle. So that looks like a pyramid with a triangular base, which is called trigonal pyramidal. Okay? Bond angle here is 109.5 because you still have four electron groups. That's the ideal bond angle. Look at the table to get more information. Let me delete this page. Okay. Now with amines, amines can be part of a ring. Don't worry, we will not have to name this, but the drug morphine, atropine, these contain nitrogen as part of the rings. These are alkaloids. They're technically naturally occurring in plants, right? So you have morphine that's used here for pain and atropine. And so we have gone through and classified amines. Now we're looking at this and we have how do we name amines? When it comes to naming amines, we do have, let's see, okay, yeah. We use this nomenclature. So the nomenclature here, we're told to name primary alkenes, sorry, to name primary amines, name the alkyl group bonded to the nitrogen atom and add the suffix amine. So name the alkyl group, name the side groups attached to nitrogen as an alkyl group, and then add the word amine. Okay? So for secondary and tertiary amines with different alkyl groups, alphabetize them like we've done before. The one with the ethyl before the methyl and then the propyl, alphabetize them. If you have for secondary and tertiary amines, if your alkyl groups are identical, use di, tri, depending on how many you have that are identical. Okay? So with this one here, this is our side group, right? Because it's attached to the nitrogen. Let me add a page here. Right, so we're dealing with CH3, NH2, NH2. So this carbon here is attached to the nitrogen, and it has 3 bonds. So this whole part here is the methyl group. The rest of this is called the amine. So methylamine. Over here, these are each side groups. Ethyl. You don't have to write the number because they're on the same not carbon, sorry, they're the same nitrogen is the first and only nitrogen. So ethyl, and then here ethyl. So we have 3 of them, ergo triethylamine. But you see how they are all stuck together as one word, triethylamine, but it's also systematic. Okay, here we have 2 different side groups. We have the ethyl side group, we have the propyl side group. So you want to alphabetize the side groups. Ethyl propylamine. So ethyl propylamine. Okay. By now, hopefully, you're seeing that these nomenclature systems follow some kind of regular pattern, right? So as we're naming these, let's see. This is our side group with how many? 1, 2, 3, 4, 5. So 5 is pentylamine, right? Right, pentylamine. What about this one here? We have a methyl here. We have a ethyl here. So arrange in alphabetical order. Ethyl, methyl, amine. Okay, that's what I think it will be. Let's see what they say. They get to it later on. Ethyl, methyl, amine. Yay. Okay, so we're going to be naming these. I'm just going to name it right here. Propylamine. This one here, we got a methyl. Here we got a propyl. So methyl propyl, wait, MNOP. Ooh, okay, yeah. Methyl propyl. I mean, for a second there, I'm like, wait a minute. M before P is those small things, right? Methyl propyl amine, right? Ooh, this one here. It's 2 of them. 1, 2, 3, 4. Butyl. So we have 2. So that should be dibutylamine. Because remember, you have 2 CH3, CH2, CH2, CH2s attached to this nitrogen. So you're going to name each of them, right? CH3, CH2, CH2, CH2. Attached to that, and you name them both. Consolidate the name, dibutylamine. Okay, now we're looking at aromatic amines. These are amines that are part of the aromatic group. We talked about this before, right? But now we're looking at it in the context where it fits. We have this one here called aniline, the benzene group plus the amine group called aniline. So this one here, because we have a side group right here on the nitrogen part, you name this part here as an alkyl, and then the rest of it will be named as an aniline. So this is the aniline part, and this is your side group. So you're just going to say ethyl aniline, right? Because the side group is in the nitrogen. Then over here, the side group is on the benzene ring. Don't worry, you won't be doing a lot of these. This is more for the majors class, but just to introduce you to the majors class, this is what we're going to be going over. So yeah, since the side group is not on the nitrogen, these are actually adjacent next to each other. Remember, this whole part combination here of atoms is called aniline. And then this one here, you could have put the number of the carbon, or you can use the letter O. Remember, O was 1, 2 combination. So You have this as carbon 1, this is carbon 2. So in the place of using 1, 2, you just use the letter O. O bromoaniline. It's like a poem. Oh, bromoaniline. Why? Wherefore art thou? Right there. Okay. Now I noticed that they did something. When I was naming this, I was wondering. Whenever the side group is part of, which I didn't mention this very clearly, whenever the side group is part of the nitrogen, they put the letter N to tell you the side group is actually on the nitrogen versus the benzene ring. When the side group is on the benzene ring, they're using the letters O, P, or M, right? Ortho, para, or meta. So here we're being asked to draw the corresponding amines. So let me start with this first one. N-methylamine. So copy that. I'll put this right here. Oh, N-methylaniline. Okay. So aniline is a benzene ring that has the NH2. Okay. But we're told that takes care of this part. But we're told on the nitrogen, you have an additional methyl group. Okay. So I have to change this then. So I'll say I do have a remaining hydrogen, but I have a methyl group right here. And of course, I have a lone pair. So that takes care of that structure. Okay. With this one here, I won't be skipping a lot because it's getting a little bit different, right? I'll just write this down. M-ethyl-aniline. B. M. Wait. Yeah. M-ethyl-aniline. Okay. Remember, meta was not adjacent, but kind of like with meta, you had at least one empty carbon between the first carbon and the third carbon, right? That was the meta position, 1 and 3. So what I'm going to do here is I'm going to draw my aniline again, benzene ring with my nitrogen on top and 2 hydrogens. That takes care of this part. They're saying this is M, so it's meta. This is carbon 1 here. So on carbon 3, I have an ethyl group, CH2, CH3. Okay, so meta just means you have, since it's aniline, you have a side group on carbon 1 and another side group on carbon 3, and that goes with meta. Okay, so, oh, this keeps going on. Okay, I'll work. I recognize that there's not a whole lot of examples out there, so I'll work on all of these. I'll be patient. Okay, let's see. I know this video is very long. Remember, you guys can you can pause and come back and watch it as much as you can. N-methylaniline. Wait, why did I copy the first one again? Did I copy the first one again? I did B. This is supposed to be C. Come on. Copy. For some reason, it doesn't copy sometimes. Okay, here. 3,5 diethyl aniline. At least I know this is not on the nitrogen, right? So I'm going to draw my aniline again. I'll do this. Okay. Diethyl, so aniline part is done. I have on carbon, oh, it's done. Hold on a second. It's done. Okay, now it's done. This is my carbon 1. This is 2. This is 3. This is 4. This is 5. This is 6. On carbon 3, I have an ethyl, CH2, CH3. On carbon 5, I have another ethyl, CH3, CH2. Okay? So aniline is done, for real. 2 ethyls are done on that position. So I am done, right? There. Then I have one more structure, so I need to add a page here. I'm trying to be linear. This one here. This is N diethyl-aniline. Okay, so I have to write that one down. N, N diethyl-aniline. aniline. Okay, for this one, my benzene ring has to be drawn. And just to be safe, I'm going to write my nitrogen here, and I'm going to put my two hydrogens here and my lone pair here. That takes care of the aniline. But they're telling me I have two side groups, two ethyls, and they are both on the nitrogen. So I have to erase this H and put one of my ethyls here, CH2, CH3, right? And then erase the other H and put my ethyl there, CH2, CH3. That takes care of everything. Aniline, diethyl on both nitrogens. Well, on both on the same nitrogen. Yeah, it takes care of that. I think I've covered everything. We can now move on to, oh, okay, physical properties, okay? So this is saying right here, many low molecular weight amines have very foul smell. We mentioned this before. Amine has that fishy smell. It smells like rotting fish and urine. You know what I found out? Okay, so I enjoy sushi, right? I enjoy me a steak and I love me some sushi too. And my friend recently got me into the real sushi. I was doing baby sushi where they cook the fish and everything. And then she's telling me, go ahead and try this. And I'm like, no, try it. Come on, be adventurous. So anyway, I go ahead and I'm like, it's gonna have a fishy taste. She says, no, it doesn't. I'm like, well, all fish smells like fish. She says, no, actually, the fishy smell you smell is because the fish is rotting. Real fresh fish doesn't have that smell. So I'm like, oh, really? Anyway, I tried it. It was tasty. Okay. I'm not saying to try it. If you're not into sushi, that's fine. But I found out through that encounter that when you smell that foul odor in fish, it's because the fish is not fresh. It has that smell, right? Anyway, so amines, the amines in the fish is the reason why you smell that smell. The chemical smell we're smelling is an amine. Amines are polar compounds. They contain CN and NH bonds. So not only are they polar, they have intermolecular hydrogen bonding. You have in your primary and secondary amines. As long as you have the NH bond, you have that intermolecular hydrogen bonding. Right. So now we're going to compare amines with other chemicals. Primary and secondary amines, because they have those hydrogen bonds via the NH bond, will have a higher boiling point. Okay. Than the other compounds that do not have the intermolecular hydrogen bonding. Example here with ether. Remember, ether has a COC bond, but not OH bond. So this one here has dipole-dipole and London dispersion force. But amine has two sites. This one here has two sites for hydrogen bond, one over there, one over there. So with two sites, of course, its boiling point is almost double this one's, right? It's higher and almost double. Okay, moving down. What about amine and alcohol? So here's where we're comparing side by side. Apparently, alcohol's intermolecular force wins. I'm impressed. Okay. Look at this. You're competing. Well, you're competing. They're comparing, right? One alcohol, one hydrogen bonding site, just one side, versus two over here. NH, and we got NH. So you see that right there? There's two NHs versus one OH. And look, the one OH wins. With just one OH, we have a much higher boiling point, right? Versus here when you have two NHs. So in other words, not all hydrogen bonds are alike. All hydrogen bonds are not alike. OH hydrogen bond is a lot stronger than the NH hydrogen bonds because even the two NH hydrogen bonds do not compare to the one OH hydrogen bond. Interesting. Okay, tertiary amines have lower boiling point because they don't have any hydrogen bond. Do you all see that right here? All the NH bonds that used to be there got broken. Well, this is a lone pair. They got broken, so they got replaced with carbons and carbons and carbons. And these carbon hydrogen bond. So look at this. This is a tertiary amine, right? With no hydrogen bonding. The boiling point is 38 degrees Celsius. With secondary amine, where you have at least one hydrogen bond, 56 degrees Celsius, 56 degrees Celsius, right? And then with primary, what was primary? Primary around 78, right? It's not as high as the alcohol. So of course, when comparing these two, I'm going to go a little faster with this part here. When you're comparing these two, with ether, of course, you know you have dipole-dipole, line dispersion force. This one here, NH, definitely hydrogen bonding, dipole-dipole, line dispersion force, okay? This one here, there's no, it's essentially N with 3 CHs, so there's no more hydrogen bonds left. For that reason, this is going to be lower, this is going to be higher. Because you see right here, this one here has got 2 hydrogen bond sites right there. This is one, this is the other. So they're saying which has a higher boiling point. This is higher, and this is higher. Higher, and then of course higher, right? What about this one here? Let's see, which compound has a higher boiling point? Definitely this one here has 2 hydrogens, right? So higher. Oh, we just saw it. We just saw this play out, right? Where OH beat 2 NHs. So I'll say this one here is higher. Because 2 H's are not a match for 1 OH. This one here will be higher because we do have 2 NHs. Here we have 2 NHs, but we know that the 1 OH beats the 2 NH. So this is a higher one, this is a higher one, this is a higher one. Okay. Okay, so right here, give me just a moment. I'll be right back. Okay, and I'm back. So now we're looking at amines, and we're being told amines are bases. They're actually weak bases, but they're bases, okay? So they are proton acceptors. They can react with something that can give protons. So the bottom line here is amines can react with acids. Because they're bases, I'll just say here, they react with acids. Okay, this is chemistry here, but I'm going to tie it into real life. No, I shouldn't say real life. Life outside of the chemistry class. Okay, amines are weak bases, so we can see here that amines will have an acid-base reaction when you have a primary, secondary, tertiary amines. Amines are weak bases compared to the inorganic base like sodium hydroxide. Sodium hydroxide is very strong. By the way, this is the base called Li. Okay, amines are a lot weaker. So we're told here that the amines will react because they're bases, right? They'll react with an acid to, again, water soluble salts. Huh? Here before, we are here again. Tertiary amine reacting with hydrochloric acid. This time the mechanism, the product we get is different. You know how I keep drawing a bond here? I keep drawing a bond because I'm used to dealing with amines. Okay? I'm used to dealing with amines that have 4 bonds versus the ones that have 3 bonds, but that's okay. Amines that has 3 bonds can actually use this lone pair here to make it a bond and form a bond with that hydrogen. So see what happens here? This lone pair gets converted into a bond to take up the hydrogen. But because it does that, nitrogen carries more bonds than it's normally used to, so it ends up being positive. Okay, this is ammonium form of nitrogen. Then the chlorine here is actually attached to this. So this whole product is technically a salt. Okay, remember the amine was a base reacting with the acid to form a salt. Okay, salts tend to be ionic. They have a positive and a negative charge, like we saw before. positive and negative charge. Okay, so real quick here, we can see once again, when the amine reacts with the acid, the product is an ammonium salt, the salt of ammonium. Ammonium is the form in which nitrogen has got 4 bonds. And you can see right here, the lone pair here that used to belong to nitrogen alone are now sacrificed to form a 4th bond with hydrogen. And then for that reason, nitrogen has to be positive because it's holding 1 extra bond than it normally does. And then the chlorine here will be left as negative. And because they're oppositely charged, they will attract. And this combination is called the ammonium salt. Okay, so do they talk about this later on? I'll talk about it right now. You know when you buy fish, if you happen to eat fish or if you hate fish because of the smell, one of the ways they actually cut that smell, because remember the fishy smell is an amine compound, right? One of the way they cut the smell is by asking you to squeeze on lemon juice. Well, guess what lemon juice has? Lemon juice has acid. So when you're pouring the lemon juice on the fish, you're essentially taking the fishy smell, reacting it with the acetic acid in the lemon juice, and producing a salt. And that salt does not have the smell of the amine. See the chemistry we do in life outside of chemistry? Right. And you squeeze that lemon on it, and squeeze some more, and you're like, ooh, this tastes so much better. Because all you're doing is reducing that fishy smell, right? Okay, so yeah, we see the positively charged ammonium ion, and together they form the salt. So, oh, okay, we're going to be doing one of these. Oh, this one here. So yeah, talking about amines, here is the methamphetamine. You know that amine that we talk about? When I say we, I mean they talk about in the news. So this is the amine, but they haven't mentioned this yet, but most amine compounds are stimulants, right? So we're looking at this right now, we're seeing it's a stimulant. So it's hard to find my amine compound here, but let me see if I can draw my product of this to get the amine salt of this right here. CH3 on top, and I got an N here, I got an H on the bottom, and I got a CH3. Oh, okay. So the H from here attaches itself right here, and then this N becomes positive, and the Cl just lingers over here, just hangs around because it's drawn to the positive nitrogen. Everybody's trying to get with nitrogen, right? The N becomes positive because it has that 4th bond. It has to have a positive charge. The Cl minus is now drawn to that positive core, so it just kind of hangs around. And together, this is called the salt. So this is a salt form of methamphetamine. So if methamphetamine wasn't made into a salt, it wouldn't have that white powder appearance. It would look more like an oily substance, very different. But it's made in the salt form, and it has that substance. And realize that this is a soluble salt, right? Anyway, yeah, we're dealing with the chemistry here. Okay. Oh. So what products are formed when each of the following amines are treated with HCl? Okay. So right here, if I add HCl, I'm trying to see if I can get my answer without having to recopy this. I'll get CH3, CH2, and gets an extra H plus a positive charge, right? And then the Cl just hangs around there, okay? Plus HCl. I'm going to write this out. Oh, it's supposed to be like this. It looks like that. CH3, CH2, the 2 outside, and gets an extra H and a positive charge. Then the Cl just hangs around as a negative. Same thing over here. What is this? I don't know what that is. HCl, CH3, CH2, the 3 of these. Okay, well, the N currently has no H. It gets an extra H plus a Cl over here. And that's it. Yeah, all of these are soluble salts. So even if they were not soluble before, for sure, when you react it with the HCl, it becomes a salt and it's soluble. Okay, let's see. Look at that. Water insoluble amine, again, is converted to a water soluble ammonium salt by treatment with acid. Once again, they're just adding an H right here, making this positive and bringing the Cl minus, and bam, we got our product, water soluble. Oh, okay. So we're doing this problem right here where it says label each compound as water soluble or water insoluble. We're trying to show you, we want you to appreciate what happened up there. Okay, this time when we have, this looks like the salt, right? This is a soluble salt format. Same thing with this. This is soluble, right? It has the same format, soluble salt format, the ammonium salt. Okay, so I'll say this is soluble, soluble, right? Because it's a soluble ammonium salt. This right here, this should be soluble because we have two hydrogen bonding sites in the structure, right? There's an N attached to an H twice, and there's only two carbons. So this is also going to be soluble. Tricky people trying to trick us to see if we're on our toes, if we're awake and paying attention. Yes, we are. Yes, we are. Yes, this is soluble because we have two hydrogen bonding sites or two polar sites, and we only have two carbons. So we're good, soluble. Okay, so focusing on life outside of chemistry, ammonia salts and their useful salts. Many amines with medical properties are sold as their ammonia salt, like I said before, which are transported through the aqueous bloodstream. Because our blood is mostly water aqueous, we want to make sure the stuff we put in the blood to work on your body is soluble. So if you can't make it soluble, solubilize it. That's not a word. That's not really a word. No. Make it soluble. That's better. So the antihistamine, Benadryl, I've used that, is sold as a salt of diphenyl. Yeah, that word. I should know how to say this, right? Diphenhydramine, right? Hydrochloride, yes. So I don't usually teach this class a lot, so I haven't been pronouncing these words quite a bit. So yeah, that's it. The point being that these salts are sold in the soluble form because your blood is aqueous. So you want to make sure the compound can dissolve in your blood, be transported, and distributed to different organs. Okay. So Benadryl is the salt version of diphenhydramine. Fun. Our final classification for this group is amide. Okay. Remember, amide looks just like amine. The only difference is the carbon here is a carbonyl carbon. We're doing good. And amides are classified based on the number of carbon atoms attached to the nitrogen atom, like we saw before. With the amine, this is considered primary, right? Because the nitrogen is attached to one other carbon, even though the other carbon is your carbonyl carbon. Part of the functional group is classified as primary amide because it's one carbon nitrogen bond. And this is abbreviated RCON, like raccoon. No, con, right? Amide usually has the CON when it's abbreviated. Okay, now here we're looking at secondary amides because we have two carbons attached to your nitrogen, right? One here, one here. This is classified as tertiary amine because we have three carbons attached to your nitrogen. One here, and then one here. Okay, so primary, secondary. Oh, when I say amine, I mean amide. We've already moved on. So we have primary amide, secondary amide, tertiary amide. Man, my mind is still stuck on the other functional group, right? All primary amides are named by replacing the oic acid with the word amide. Okay, so you want to, once again, following this rule here works better when you're dealing with the special names, like with the benzoic acid. This would be benzamide. Benzoic acid will form benzamide. Acetic acid will form acetamide. So this works better going this process if you're dealing with a molecule that's named with a common name versus a systematic name. You go from acetic acid to acetamide or acetamide, benzoic acid with benzamide or benzamide, depending on, British or American pronunciation. Okay, so when we're trying to name an amide that has two side groups, as in secondary or tertiary amide, name the alkyl groups bonded to the nitrogen atom and use the prefix N. Remember, N symbolizes this side group is attached to the nitrogen, preceding the name of the alkyl group. Name the RCO as an amide, okay? So when we're naming this one here, I like to draw it out. So I have a carbonyl H O N. Oh, I feel like I'm running out of space already. Hold on. N. Yeah, there's one. This is one. H. CH2. CH3. Okay. Work, people. Okay. So this is a functional group here. And this functional group gets called amide or amide. And this is our side group. And this gets called ethyl. But it's on the nitrogen, so it gets called N-ethyl. Right? So N-ethyl. Ooh, hold on a second. I forgot something. I forgot one thing. This is amide. We have to look at how many carbons we have on this side. We only have one carbon. Ooh, yeah, I'm a little rusty, y'all. We only have one carbon here. So that's going to be formamide. Like formaldehyde or formic acid. Yes. Okay. So let's go over here and see how they did this. Right. So they went from naming this, the original formic acid they're talking about looks like this. This is what formic acid is. And so remember, this group here is replaced with all of this. So when you're naming this, you want to name the formic acid first, replace the ic acid with amide. And so the overall name becomes N-ethyl, that's the side group, formamide. Yeah, this part is not the easiest part. I'm a little rusty even in the nomenclature. I'm gonna stick with the what is it called? The technical names versus the more casual names. Formamide is a casual name. Right. Okay. So here we don't have any side groups on the nitrogen, but we have 1, 2, 3, 4, 5 carbons. Let me see. Oh, since we have a regular compound here, regular amide, I'm going to try to see if I can just replace the E with a pentane, right? I have 1, 2, 3, 4, 5 carbons. Replace the E with amide. So that would be pentanamide. The longest chain will be pentanamide. And then I guess that's it. Because I don't have any side groups here. I thought I had a side groups. Oh, okay. Pentanamide. I don't have any side groups, to be it. Pentanamide. This one here, I do have a side group. And then the rest of this is derived from benzoic acid. So benzoic acid, I'll write here, benzoic acid was the acid this is derived from. Replace the oic acid according to the rules they're saying, and then add amide. So benzamide is the longest chain, right? And then the side group here is N-methyl. N-methyl benzamide. Trying to make sure that they did talk about benzamide back here, right? Okay. This last one here, oh wow, again, this short group here comes from formic acid. So replace ic acid with amide, so it becomes formamide, right? That becomes the name of this part here. And then the side groups is propyls, but two propyls. So we have N, comma, N dash di propyl. I know this is very different. Like I'm having to think to remember how we do the systematic format. Okay, N, comma, N dash dipropyl formamide. Woo! Okay, following the process, right? Okay, this should be a lot easier because we are going, they're giving us a name. They're doing the hard work and we're just trying to draw the picture, right? So propanamide, this is the same thing as, not same thing, it's synonymous, similar to propane, right? So we need an amide with 3 carbons. 1, 2, 3. And then bring in your nitrogen here. Since there's no side group, you bring in your hydrogen here, and then draw in your CH2, CH3. That's this, and this is done. Let me shrink this. Okay? For the first one. The second one, we have N-ethyl-hexanamide. Okay? Hexanamide is like hexane, so we have how many? We have 6 carbons. 1, 2, 3, 4, 5, 6. The 6th carbon has our functional group, but it says right here, oh, I should make this smaller. It says right here, there's an ethyl group attached to the nitrogen, so CH2, CH3. That takes care of that, it takes care of that. So I can just fill in the rest. Put a hydrogen here, put a H up, H bottom, H up, H bottom, H up, H bottom, H up, H bottom, H up to the left and to the bottom. Woo! Made it. Last one is acetamide. They're using the common name. Aceta means 2 versus let's see, meth S. F is a more technical term. Acetamide is a common term. So this means 2 carbons. Okay. So middle carbon, the carbon with the functional group right here. Okay. CH3. On the nitrogen, we have 2 things attached, 2 methyls. So we have a methyl group right here. We have a methyl group right here. I've been leaving out the lone pairs, y'all. Go back and put the lone pairs on this. I've been leaving them out. Bad, bad. Yeah. N, comma, N dimethyl. That's that. Okay. You want to be familiar with these because as you can see, they're using a little bit of the common language in the systematic nomenclature. So you want to be aware of it because it does make life easier for you. Okay, as we're going through these, we're told primary and secondary amides have higher boiling points than tertiary amides and even esters. Why? Same thing. It all boils down to intermolecular hydrogen bonding. See, ester has a boiling point of 58 degrees Celsius. This tertiary amide is 153 degrees Celsius. Wow, look at the difference, right? Primary amide, 213 degrees Celsius. Man, this is way hotter than water. Okay, this is a whole different level. Okay. But it has 2 hydrogen bonding sites here. And then this one here can also hydrogen bond, right? With a hydrogen if you have a flipped version of the molecule. Okay. So let's see. Oh, we're doing good. We're close to the end. Treatment of an amide with water in the presence of acid catalyst forms the carboxylic acid and the ammonium salt. So when we're dealing with derivatives of carboxylic acid, to make the amide, we start off with the carboxylic acid. When we add water to it, we're getting the reactant back. So when we're adding water, just like before, right? This time, the leaving group, the teacher who is leaving, by the way, this is a substitution reaction. Substitution. Again, the leaving teacher is the amine group. The one that's coming in to replace it is the OH, like we saw before, right? So the OH, or sorry, the leaving group, the amide leaves, the nitrogen part goes away, and then the OH comes in to replace it. And meanwhile, this one and this reconnect over here to form the ammonium salt. And then in this process here, we reclaim or reform the carboxylic acid. Okay? Oh, so we're doing that here. Guys, we're close to the end. Okay, I shouldn't get too excited. Okay. No, I am excited. I won't hide my excitement, okay? I'm excited. Okay. So here we have once again leaving. Oh, I can't see what's leaving here. We'll figure it out. Something there is leaving. Okay, the whole thing is this is leaving. So our product then will be, let me try to see if I can find an easy way, y'all. Easy way. I just copy part of this. Copy. Paste. Haha. Okay. Okay, this is not lazy. This is innovation right here. So the group coming in is an OH, and of course the NH2 leaves off with H, right? As NH3. Okay, same thing over here. You add H dash OH. Oh, they said use acid. Oh, I forgot the acid. H2SO4. Okay. Once again, yo, let me be innovative and try to, because it's a lot easier to just copy this. Well, for me, and to, oops, I have the wrong setting on. I'm trying to get through this part faster, because copy. Oh, my coworkers. Okay, hold on. So the OH comes in and goes to that spot right there, and then the rest of the molecule, the NHCH3 gets attached to the H, right? With this one here, I'm going to draw this out like this, and then we're about to wrap this up. And then CON, carbonyl dash N. Then we have two of these, CH2, CH2, CH3, CH2, CH2, CH3. That's a huge leaving group to leave, right? The bond has to break right here, and then let this go off. And so, of course, if that happens, oh, that's a lot to rewrite. If that happens, this goes over here on one side. And then, of course, over here, you see the OH come in. So this would be our product when you add H2O and sulfuric acid. The OH comes in over here, and then the H comes in over here. And this becomes our product. Okay? Oh, so this is our last slide. We're told that caffeine and nicotine are widely used stimulants of the central nervous system. They contain nitrogen atoms in rings. They're called alkaloids and naturally occurring amines derived from plants. So, of course, you have caffeine, nicotine, and amphetamine. But they're all amine compounds that stimulate the nervous system, right? I had to throw that one in there, y'all. But yeah, we're talking about the functional groups and how they all go together, right? So amine compounds tend to be compounds that stimulate the nervous system. Okay? Think about caffeine, think about nicotine, and think about the other anes. This is the end, guys, just in time. I have 10 minutes before it starts. Okay? Thank you all. Thank you for surviving. You can watch this later on because that was a lot of information. Okay, thanks. You too.